Git Demystified, your practical guide to version control. Chapter 1, The World Before Git, Why Version Control Matters. The Unseen Heroes of Software. Imagine you're writing a book. You start with Chapter 1, then revise it. Then you write Chapter 2. Suddenly, you realize that a character you introduced in Chapter 1 needs to be removed. You find the first draft, make the change, and then copy and paste the rest of the book over. But what about the changes you made to Chapter 2? Did you remember everything? Did you accidentally delete a paragraph in Chapter 3? Now, imagine doing this with hundreds or thousands of pages, shared among several co-authors, all working simultaneously. One author might be rewriting a section, another might be fixing a typo, and yet another might be adding new content. Without a systematic way to track who changed what, when, and where, you'd quickly descend into a chaotic mess of overwritten files and lost work. This is precisely the challenge faced by anyone creating software, managing website content, designing hardware, or even drafting legal documents. This chaotic reality isn't a hypothetical. Ask any experienced developer, and they'll likely share stories of lost code, accidentally overwritten features, or the dreaded moment when a final version of a file inexplicably broke everything. The struggle often manifested as files named project_final_zip, project_final_2, zip, project_final_zip, and sometimes, horrifyingly, project_final_zip. Each file represented a desperate attempt to save a specific state of the project, a fragile snapshot that could easily be corrupted or misplaced. Worse still, if a critical bug appeared, trying to pinpoint when it was introduced, and by whom, was like searching for a needle in a haystack made of endless, poorly labeled files. This messy past highlights a critical need, a need that version control systems were designed to fulfill. What is version control, VCS SCM? At its heart, a version control system, often called a VCS or source code management, SCM system, is a tool that records changes to a file or set of files over time. This allows you to recall specific versions later. Think of it as an incredibly detailed history book for your project, meticulously documenting every single alteration, addition, and deletion. The benefits of using a VCS are profound and transformative for any collaborative or evolving project. History tracking: every change is logged, along with who made it, when, and often why. This provides an invaluable audit trail. Collaboration: multiple people can work on the same files concurrently without overwriting each other's work. The system helps manage and combine their changes. Rollback undo: made terrible changes, introduced a nasty bug. A VCS allows you to easily revert to any previous stable version of your project or even individual files. It's like having an unlimited undo button for your entire project history. Branching: developers can diverge from the main line of development to work on new features or bug fixes in isolation. This allows for experimentation and parallel development without destabilizing the main project. Conflict resolution: when multiple people change the same part of a file, a VCS provides tools to help you identify and resolve those conflicts, merging the changes harmoniously. Auditability and accountability: you know who changed what, which is crucial for debugging, code reviews, and meeting compliance standards. In essence, a VCS turns a chaotic free-for-all into an organized, trackable, and recoverable process. It's the save game system for your code, ensuring that no progress is truly lost and that you can always return to a known good state. A brief history of version control: the concept of tracking changes is not new, but the methods have evolved significantly. Local version control systems: in the early days, some developers used simple local VCS. These systems stored revisions on the developer's local computer. One example was the Revision Control System, RCS, which was popular in the Unix world. While better than nothing, their major limitation was their inability to handle collaboration. If you wanted to share changes with another developer, you'd have to manually copy files over, often leading to the my_code_final_zip problem we discussed. Centralized version control systems, CVCS. The next major leap was the advent of centralized version control systems. Tools like CVS, Concurrent Version System, and Subversion, SVN, became the norm. With a CVCS, there's a single, central server that hosts all the versioned files. Developers check out files from this central repository, make their changes, and then commit them back to the server. How they work. All operations, checking out, committing, merging, require a connection to the central server. Pros: simpler to set up initially, and everyone works from a single source of truth. Cons: the single central server is a single point of failure. If the server goes down, no one can work, commit changes, or access the project history. Furthermore, working offline is impossible, and merging changes, especially between different features, could often be complex and error-prone. Imagine a central library where you must check out every book to read it, and if the library is closed, you can't read anything. CVCS systems were a huge step forward for collaboration, but their limitations highlighted the need for something even more robust and flexible. Distributed Version Control Systems, DVCS. This brings us to distributed version control systems, where Git stands as the undisputed leader, alongside others like Mercurial. DVCS fundamentally changes the game by giving every developer a full, complete copy of the project's entire history. How they work. When you clone a repository, you don't just get the latest version of the files. You get the entire history of the project. This means almost all operations, committing, branching, viewing history, can be performed locally without needing to interact with a remote server. Pros: no single point of failure. If the central server, or remote repository, goes down, every developer still has a complete backup. Work can continue as usual, and changes can be pushed to a new server or another developer's repository later. Offline work. Since your entire history is local, you can work, commit, and manage branches anywhere, even without an internet connection. Speed. Most operations are performed on your local machine, leading to incredibly fast performance. Powerful branching and merging. DVCS, and especially Git, are designed from the ground up for agile, nonlinear development. Branching and merging are core, lightweight operations. Cons. Initially, the conceptual model can be a bit more complex to grasp, and local repositories can take up more disk space for very large projects. Imagine everyone having their own complete copy of the library, including all its historical revisions. You can read, organize, and even add new books without ever needing to connect to a central library system. Why Git? The rise of a leader. Git was created in 2005 by Linus Torvalds, the creator of the Linux operating system kernel. He needed a lightning-fast, highly distributed version control system that could handle the immense scale and rapid pace of Linux kernel development, which involved thousands of developers worldwide. When existing CVCS solutions proved inadequate, he famously built Git in just a few days. Git's design principles were revolutionary at the time and continue to define its success. Speed. Designed to be incredibly fast, even with large projects. Simplicity. While its internal model can seem complex, its core commands are straightforward, distributed, rooted in the idea that every developer has a full copy of the repository. Nonlinear development, built to make branching and merging easy, encouraging parallel work. Cryptographic integrity. Every bit of data in Git is checksummed using SHA-1 hashing, ensuring that content cannot be corrupted or subtly changed without Git detecting it. This provides an almost unparalleled level of data integrity. Compared to its predecessors, Git offered immediate and compelling advantages. Unmatched speed. Local operations are nearly instantaneous. Robustness. Thanks to its content-addressable file system, which we'll explore in Chapter 2, Git is incredibly resilient to data corruption. Scalability. It effectively manages projects from small personal scripts to gargantuan endeavors like the Linux kernel itself. Powerful branching and merging. Git truly excels here, enabling workflows previously unimaginable with CVCS, fostering rapid development and experimentation. Today, Git is the de facto standard for version control in software development. It's used by millions of developers, powers platforms like GitHub, GitLab, and Bitbucket, and underpins countless open source and commercial projects. Its prevalence means that understanding Git is no longer just a nice-to-have skill for developers, it's a fundamental requirement. Setting expectations, what you'll learn. This book is your practical guide to navigating the world of Git. We'll start with the fundamentals, making sure you grasp the core concepts that make Git so powerful. Then, we'll move into the daily commands you'll use constantly, covering everything from making your first commit to collaborating with a team on complex features. We will focus on the why as much as the how. Understanding Git's underlying logic will save you headaches and empower you to troubleshoot effectively. Whether you're an aspiring developer, a project manager, a technical writer, or anyone who collaborates on digital assets, this book will equip you with the knowledge and confidence to leverage Git effectively. Summary and looking ahead. You've now seen why version control is indispensable in today's collaborative digital landscape, and how Git, as a distributed system, offers significant advantages over its predecessors. We've established that Git isn't just a set of commands. It's a powerful framework built on specific design philosophies that enable speed, integrity, and highly flexible workflows. In the next chapter, we'll dive deeper into these foundational concepts, exploring Git's unique way of storing information and managing history. Understanding these core ideas will demystify many of Git's powerful capabilities and pave the way for you to master its practical applications. Chapter 2, Git's Foundations, Understanding the Core Concepts. Introduction, Beyond the Commands, the Git Mindset. You've installed Git, maybe even made a quick first commit. But perhaps you've also heard whispers about strange Git behaviors or commands that seem to do magical or terrifying things. To truly harness Git's power and avoid common pitfalls, it's not enough to just memorize commands. You need to understand Git's underlying philosophy, its mindset. Most version control systems you might have encountered, especially older centralized VCS like Subversion, primarily think in terms of changes or deltas. They store a base version of a file and then record only what changed from one version to the next. Git, however, operates fundamentally differently. It thinks in snapshots. This distinction is crucial, and once you grasp it, many of Git's seemingly complex behaviors begin to make perfect sense. Snapshots, not deltas, Git's unique approach. Imagine you're documenting a project. A traditional delta-based system might say, version 2 is version 1 plus these 5 lines. Version 3 is version 2 minus these 3 lines and plus these 10. If you want to reconstruct version 3, the system has to start from the base and apply all the subsequent changes. Git, on the other hand, doesn't store changes. Instead, when you commit, Git takes a picture of what all your files look like at that exact moment. It stores a reference to that complete snapshot of your entire project directory. If a file hasn't changed since the previous snapshot, Git doesn't store a new copy of it. It just links to the previous identical file. But conceptually, for each commit, it's as if Git saves a full, distinct copy of your entire project. This snapshot-based approach offers tremendous advantages. Speed. Reconstructing any version is fast because Git simply points to the full snapshot rather than replaying a long history of deltas. Integrity. Each commit represents a complete, self-contained state of your project. This makes your history incredibly robust against corruption. Flexibility. It makes operations like branching and merging far more efficient and powerful, as Git is designed to easily track and combine distinct project states. Think of it like this. Instead of writing down, Chapter 2 had 5 words added on page 3 and a paragraph removed on page 7. Git simply saves, here is the complete Chapter 2 as it stands now, including all text and formatting. Every time you change anything and commit, Git effectively snaps a new picture of your entire project. The content addressable file system. To efficiently store these snapshots, Git employs a clever trick. It uses a content addressable file system. This is a fancy way of saying that Git stores everything as objects, and each object is uniquely identified by its content. Here's how it works. When you add a file or any piece of data to Git, Git calculates a unique identifier for that content. This identifier is a 40-character string called a SHA-1 hash, Secure Hash Algorithm 1. For example, a file's content might produce a hash like 83 ba 61802, E4BC 24D6V1, DTB 7B 512, ED 7C4E. This SHA-1 hash becomes the key to retrieve the content. If the content of a file never changes, its SHA-1 hash will always be the same. If two files have exactly the same content, even if they have different names or are in different directories, Git will only store that content once. It just creates two pointers to the same stored object, saving space and ensuring integrity. This cryptographic hashing is why Git is so robust. If even a single byte of stored data is corrupted, its SHA-1 hash would change, and Git would immediately detect that the integrity of your project history has been compromised. This ensures that the history you're viewing is exactly the history that was stored. Core Git objects, the building blocks of history. Git builds your project's history using 4 fundamental types of objects, all identified by their SHA-1 hashes and stored in the hidden Git directory. Blob binary large object. What it is? A blob object simply stores the content of a file. It doesn't contain any information about the file name, permissions, or directory structure. It's just raw data. Analogy: a digital photograph of a page of text, stripped of its file name. Example: if you have a file hello.txt containing hello world, Git computes the SHA-1 of hello world and stores that content as a blob. Tree object. What it is? A tree object represents a directory. It stores a list of references to other tree objects, subdirectories, and blob objects, files, along with their file names and permissions. It's essentially a directory listing for a specific point in time. Analogy: a folder icon that contains references to files or other subfolders. Example: a tree object for your project's root directory would contain entries like 100,644 blob SHA, one of hello.txt's blob hello.txt, 40,000 tree SHA, one of src Dyer's tree src/. Commit object. What it is? The commit object is the most important for understanding your project's history. Each commit object represents a single, complete snapshot of your project at a specific moment. What it contains: a pointer to the single top-level tree object that represents the state of your entire working directory at the time of the commit. The SHA-1 hash of its parent commits. This is how Git builds its history. Each commit points back to the commits that came immediately before it. Most commits have one parent, linear history. Merge commits have 2 or more parents. Metadata. Information about the commit, including the author's name and email, the committer's name and email, the timestamp, and the commit message. Analogy: a meticulously labeled box that contains a complete snapshot of your project, along with a note indicating where it came from its parent. Tag object. We'll cover these more thoroughly in Chapter 10, but briefly. What it is: a tag object simply points to a specific commit object. They are often used to mark specific points in history as important, like release versions, e.g., v1.0.0. Analogy: a permanent sticky note attached to a specific snapshot in your project's history. The relationships between these objects are what form your Git history. A commit object points to a tree object, which in turn points to blob objects, files, and other tree objects, directories. By following these pointers, Git can reconstruct the exact state of your project at any given commit. The 3 states and 3 areas of Git. Another fundamental concept in Git is understanding how files move through different states and locations within your workspace when you're making changes. Think of it as a life cycle for your modifications. Git divides your project into 3 main areas, and files can be in one of 3 states within these areas. The 3 areas or trees: working directory or working tree. What it is: this is the actual set of files and directories on your computer that you can see and edit. It's the version of your project you're currently working on. Analogy: your physical desk where you do your work. Staging area or index. What it is: this is a temporary snapshot of what your next commit will include. It's a lightweight, intermediate holding area where you collect changes you want to commit together. Analogy: a whiteboard where you perfectly arrange the changes you want to package together for the next delivery. Only what's on this whiteboard will be included in the next package. Git directory or repository. What it is: this is where Git stores all of its objects, blobs, trees, commits, metadata, and history. It's the core database of your project, usually residing in the hidden Git folder within your project directory. Analogy: A locked vault where all the official, stamped, and archived versions of your project snapshots are stored. The 3 states of your files. As you work, your files will naturally cycle through these 3 states. Modified, where it is, in your working directory. What it means: you've made changes to a file, but you haven't yet told Git to consider those changes for your next commit. The file in your working directory is different from the version Git has in its database or in the staging area. Staged, where it is, in the staging area. What it means: you've explicitly marked a modified file to be included in the next commit. Git has taken a snapshot of this file's content and placed it in the staging area, ready to be written to the Git directory. Committed, where it is, securely stored in the Git directory, your local repository. What it means: the staged changes have been permanently recorded as a snapshot, a commit object in your project's history. Here's the typical flow. You modify files in your working directory. You use git add to tell Git to move the current state of those modified files from your working directory into the staging area. Now they are staged. You use git commit to tell Git to take everything currently in the staging area and convert it into a permanent commit object in your Git directory. Now those changes are committed. Understanding this cycle is fundamental to using Git effectively. It explains why you need to git add before git commit and how you can selectively commit only certain changes from your modified files. Pointers. Head, branches, and remotes. Git's history is built as a directed acyclic graph, DAG, of commit objects, where each commit points back to its parents. But how do you navigate this history? Git uses pointers, simple labels that point to specific commits. Commit pointers, SHA-1 hashes. As we've seen, every commit has a unique 40-character SHA-1 hash. You can always refer to a specific commit using its full hash or often the first few characters, as long as they are unique enough. Branches. What it is: a branch in Git is simply a lightweight, movable pointer to a commit. By default, when you initialize a new repository, Git assigns the name main or historically master to the first commit you make. How it works: when you create a new commit, the branch pointer automatically moves forward to point to this new commit. This is how a branch grows. Analogy: imagine a post-it note stuck to a specific commit. When you make a new commit, you peel off the post-it and stick it onto the new commit. Head. What it is: head is a special pointer that indicates which branch or commit you are currently working on. It's essentially what you have checked out. How it works: most of the time, head points to a branch, e.g., head points to main. When head points to a branch, Git knows that when you make a new commit, it should advance that branch pointer. Detached head, state. Sometimes, head can point directly to a commit instead of a branch. This is called a detached head state. It means you're not on any particular branch, and any new commits you make will not automatically advance a branch pointer, potentially leaving them unreachable by branch names unless you explicitly create a new branch there. Don't worry, we'll cover how to handle this safely in Chapter 8. Remote tracking branches. What it is: when you interact with remote Git repositories, like those hosted on GitHub, Git maintains remote tracking branches. These are not branches you can directly work on. Rather, they are bookmarks that tell you the state of specific branches on the remote repository as of your last communication with it. Example: if you clone a repository from GitHub, you'll likely have a remote named origin. Git will then create local remote tracking branches like origin main, meaning the main branch on the origin remote. Origin main always shows you where main was on the origin remote the last time you fetched or pulled from it. These pointers allow you to effortlessly switch between different versions of your project, create new lines of development, and track the progress of collaborators, all without duplicating large amounts of data. Summary. The Git structure explained. Git's power comes from its unique blend of these core concepts. Snapshots, not deltas. Every commit is a full picture of your project. Content addressable storage. Data is stored and retrieved by its unique content hash, ensuring integrity. Fundamental objects. Blobs, trees, and commits form the building blocks of your project's history. 3 areas states. Understanding the working directory, staging area, and Git directory, and how files move between modified, staged, and committed states clarifies your daily workflow. Pointers. Head, branches, and remote tracking branches are lightweight labels that navigate your project's history with incredible flexibility. While these concepts might take a moment to sink in, they are the key to truly understanding how Git works. Instead of just memorizing commands, you'll begin to intuit why certain commands exist and what they are doing internally. In the next chapter, we'll move from theory to practice, showing you how to install Git on your system, configure it, and perform your very first commits, putting these foundational concepts into action. Chapter 3, Getting Started. Installation, configuration, and your first repository. Introduction, your first steps into version control. With the theoretical foundations of Git firmly in place, it's time to move from concepts to concrete action. This chapter will guide you through the essential first steps. Installing Git on your computer, configuring it so your commits are properly attributed to you, and finally, creating your very first version-controlled project, either from scratch or by cloning an existing one. While many graphical user interface (GUI) tools exist for Git, we will focus on the command line interface (CLI) for explanations. Understanding the CLI is crucial because it gives you the most direct control over Git, provides the clearest insight into its operations, and is universally applicable regardless of your operating system or preferred graphical tool. Once you master the fundamentals via the command line, using a GUI becomes much more intuitive. Installing Git. Installing Git is a straightforward process on most operating systems. We'll cover the common methods for Windows, Mac OS, and Linux. Installing Git on Windows. The easiest way to install Git on Windows is to download the official installer from the Git website. Download. Open your web browser and navigate to https://git-scm.com/download/win. The download should start automatically within a few seconds. Run the installer. Once the download is complete, locate and double-click the downloaded exe file. Follow the wizard. The installer will guide you through several screens. For most users, accepting the default options is perfectly fine. Select Components screen, ensure Git Bash here and Git GUI here are checked, as these add convenient right-click context menu options in File Explorer. Adjusting your path environment screen. The recommended option, Git from the command line and also from third-party software, is generally the best choice as it allows you to use Git commands from any command prompt. Choosing the default editor used by Git screen. Select your preferred code editor, e.g. Visual Studio Code, Notepad++, Sublime Text. If you're unsure, use Vim, the default, is acceptable for now. Choosing how Git SCM should be invoked from command line screen. Keep the default, use bundled OpenSSH, unless you have a specific reason not to. Choosing HTTPS transport backend screen. Keep the default, use the OpenSSL library. Configuring the line ending conversions screen. Keep the default, check out Windows style, commit Unix style line endings. This will prevent issues when collaborating across different operating systems. Configuring the terminal emulator to use with Git Bash screen. Keep the default, usemin_tty, the default terminal of MSYS2. Choose the default behavior of Git pull screen. The default fast forward or merge, is generally fine for beginners. Choose a credential helper screen. The default Git Credential Manager core is recommended for securely storing credentials when interacting with remote repositories. Configuring extra options screen. Leave the default Enable File System Caching and Enable Symbolic Links unless you have specific needs. Configuring experimental options screen. Leave all experimental options unchecked unless you specifically want to try something advanced. Finish installation. Click Install and then Finish. Verify installation. Open your command prompt, cmd or git bash, search for git bash in Start menu. Type Git version and press Enter. You should see the installed Git version number, e.g., Git version 2.40.1 Windows.1. If you see a version number, Git is successfully installed. Installing Git on Mac OS. For Mac OS users, there are a few common ways to install Git. Xcode command line tools. If you don't have Git installed, simply opening your terminal application and typing Git version will often prompt you to install the Xcode command line tools, which includes Git. This is the simplest method for many users. Open Terminal, Applications Utilities Terminal. Type Git version and press Enter. If you don't have it, a dialog box will appear asking if you want to install command line developer tools. Click Install. Alternatively, you can install the full Xcode IDE from the App Store, which includes these tools. Homebrew, recommended for developers. Homebrew is a popular package manager for macOS that simplifies installing command line tools. Install Homebrew. If you don't have Homebrew, open Terminal and paste the command from https://brewsh/ and press Enter. Follow the on-screen instructions. Install Git with Homebrew. Once Homebrew is installed, simply type brew install Git in your terminal and press Enter. Verify installation. After either method, open Terminal and type Git version and press Enter. You should see the installed Git version. Installing Git on Linux. On most Linux distributions, you can install Git using the distribution's package manager. Debian/Ubuntu/pop OS, open your terminal, update your package lists. Sudo apt update. Install Git, sudo apt install Git. Fedora, open your terminal. Install Git, sudo dnf install Git. CentOS RHEL, open your terminal. Install Git, sudo yum install Git. Arch Linux, open your terminal. Install Git, sudo pacman sgit. Verify installation. After installation, open your terminal and type Git version and press Enter. You should see the installed Git version. Initial configuration. Setting up your identity. Now that Git is installed, you need to tell it who you are. This is crucial because every commit you make in Git is associated with an author name and email address. This personal information is embedded within the commit object, as discussed in Chapter 2, and becomes part of the project's permanent history. We'll use the git config command to set these details. Git has multiple levels of configuration. System applies to all users on the computer /etc/gitconfig. Global applies to your user account across all your Git repositories /gitconfig or /config/git/config. This is what we'll use for user identity. Local applies only to the current repository git/config within a specific project. To set your identity globally recommended as it applies to all your projects. Set your username. Git config global user.name your name. Replace your name with your full name as you want it to appear in your commits. For example, Jane Doe. Set your user email. Git config global user email. Your email at example.com. Replace your email at example.com with the email address you want associated with your commits. This is often the email associated with your GitHub or GitLab account. Set default branch name, optional but recommended. Historically, the default branch name was master. However, main is now a widely adopted and more inclusive term for the default primary branch. You can configure Git to use main for all new repositories you initialize. Git config global init.default branch main. Checking your configuration. To verify that your settings have been applied, you can list all your global configurations. Git config global list. This will show you entries like user.name equals your name and user email equals your email at example.com. You can also query specific values. Git config user.name. Git config user email. Configuring your default text editor optional. When Git needs you to compose a multi-line message, like a commit message when you don't use the M flag or a rebase operation, it will launch a text editor. By default, this is often Vim, which can be daunting for newcomers. You can configure Git to use your preferred editor, Visual Studio Code, Git config, Global Core Editor, Code Weight, Sublime Text, Git config, Global Core Editor, Subl NW, Notepad++, Windows, Git config, Global Core Editor, C/program files /notepad++/notepad++, exe, multi-inst notabar, no plugin. Note: adjust the path to your Notepad++ executable if it's different. To disable the custom editor and revert to Git's default, Git config global unset core editor, creating a new local repository. Git init. You have Git installed and configured. Now, let's start a brand new project and bring it under Git's control. Imagine you're starting a new website project called My Website. Create a project directory. Open your terminal or command prompt and navigate to where you want to create your project, e.g., your Documents folder, or a dedicated Projects folder. mkdir My Website. cd My Website. This creates a new folder named My Website and changes your current working directory into it. Initialize a new Git repository. Once inside the My Website directory, tell Git to initialize a new, empty repository here. Git init. You will see a message like, initialized empty Git repository in path to my website Git. What just happened? Git created a hidden directory named Git inside your My Website folder. This Git directory is your repository. It contains all the Git objects, blobs, trees, commits, refs, pointers like branches, and configuration that Git needs to manage your project. You generally should not manually modify anything inside the Git directory. Your My Website folder is now what Git calls a working directory associated with this new repository. Cloning an existing repository. Git clone. Often, you'll start working on a project that already exists, perhaps hosted on a service like GitHub, GitLab, or Bitbucket. In this case, you don't initialize a new repository. You clone the existing one. Cloning downloads a full copy of the entire project history from a remote server to your local machine. Let's try cloning a public repository from GitHub. For example, a simple Hello World repository. Find a repository to clone. Go to a public GitHub repository. You can search for GitHub Hello World example, or use a known one like https github.com/octocat/spoon-knife. Look for the code button, usually green, and copy the https URL e.g. https github.com/octocat/spoon-knifegit. Clone the repository. In your terminal, navigate to the directory where you want to place the cloned project, e.g., your projects folder, but not inside your My Website project. cd. Assuming you're still in My Website folder, go up one level. Git clone https github.com/octocat/spoon-knifegit. You will see output indicating that Git is cloning, receiving objects, resolving deltas, etc. Once complete, you'll have a new folder named Spoon Knife, or whatever the repository's default name is in your current directory. What Git clone does, it downloads a copy of the entire Git directory, the full history, and all objects from the remote server. It checks out the latest version of the project into a working directory. It automatically sets up a remote named origin by default that points back to the URL you cloned from. This allows you to easily push and pull changes from the original repository. It creates a local branch, usually main or master, that tracks the remote's default branch. Now, navigate into the clone directory. cd Spoon Knife. You can now see the project's files within this directory. This is your local working copy of the remote repository. Your first commit, adding files to history. Whether you initted a new repository or cloned one, the next step is often to make some changes and save them into Git's history. Let's work with our My Website project for this. Navigate to your project directory, cd path to My Website hash, or, if you're already there, skip this. Create a sample file. Use your preferred text editor, like VS Code, Notepad, or even Nano in the terminal, to create a simple file inside your My Website directory. Let's call it index.html. Add some basic HTML content to it. Diositoip HTML. HTML lang equals n. Head, meta charset equals UTF-8. Meta name equals viewport, content equals, width equals device width. Initial scale equals 1.0. Title my first website title. Head, body, h1 hello from Git, /h1. P this is my first version controlled website P. Body, HTML. Save the file. Check the status of your repository. This command is your best friend in Git. It tells you what's going on in your working directory and staging area and what Git is aware of. Git status. You should see output similar to this. On branch main. No commits yet. Untracked files. Use git add file to include in what will be committed. Index.html. Nothing added to commit but untracked files present. Use git add to track. Git correctly identifies index.html as an untracked file. This means Git sees it in your working directory, but it's not yet part of your repository's history, nor is it in the staging area. Stage the file. To tell Git you want to include index.html in your next commit, you need to add it to the staging area. Git add index.html. You can also use git add to stage all new and modified files in the current directory and its subdirectories. Be careful with git add in larger projects, as you might stage files you didn't intend to. For now, git add index.html is precise. Check status again, git status. Now the output should be different. On branch main. No commits yet. Changes to be committed. Use git rm cached file to unstage. New file, index.html. The message, changes to be committed under new file, index.html, indicates that index.html is now in your staging area, ready to be committed. Commit the file. Finally, you create a commit, which is a snapshot of everything in your staging area, along with your commit message and identity. Git commit m, initial commit of index.html. The m flag allows you to provide a short, one-line commit message directly on the command line. Good commit messages are descriptive and explain what changes were made and why. Git will respond with something like, main root commit, b1a to c3d initial commit of index.html. One file changed, 12 insertions, plus. Create mode 100,644, index.html. The b1a to c3d is a shortened version of the unique SHA1 hash for your commit. Check your commit history to see the history you've created. Use git log. You will see details about your newly created commit, including the author, date, and your commit message. Commit B1A to C, 3D6 C7 D8 E9, F0, A1B to C3 D4 E5, F6 A7 B8 C9 D0 E1 F2. Headman. Author, your name, your email at example.com. Date, monoct 26/10/00, 2023-500. Initial commit of index.html. Congratulations! You've successfully installed Git, configured your identity, created a new repository, Git init, added a file to the staging area, Git add, and recorded your first snapshot in Git's history, Git commit. If you cloned a repository, you've also seen how to bring an existing project under your local control. Summary and next steps. You've taken the essential first steps in your Git journey. You now have Git running on your machine, configured to know who you are, and you've created or cloned a repository, saving your first changes into its history. In the next chapter, we'll dive deeper into your daily interactions with Git. You'll learn more about Git status, how to view differences in your files, what makes a good commit message, and how to effectively manage ignoring files you don't want Git to track. This will equip you with the fundamental commands for tracking your local project's evolution. Chapter 4, Your Daily Workflow, Tracking Changes and Committing History. Introduction, the rhythm of version control. In the previous chapter, you installed Git, configured your identity, and initiated your first repository. You even made your very first commit. Now, it's time to settle into the rhythm of daily Git usage. The commands you're about to learn form the core of your interaction with Git, enabling you to track your progress, capture meaningful milestones, and confidently manage your project's history. This chapter focuses on the routine commands you'll use almost constantly. Checking what's changed, staging your desired modifications, reviewing differences, and committing those changes to your repository. We'll also cover how to prevent unwanted files from cluttering your Git status using gitignore. Checking repository status. Git status. The git status command is your compass when navigating the Git landscape. It provides a clear, concise overview of the current state of your working directory, staging area, and repository. It tells you what branch you are currently on, which files you have modified but aren't yet staged, which files are in the staging area, ready for the next commit, which new files are present in your working directory but are not yet tracked by Git. If your local branch is synchronized with its remote counterpart, more on this in Chapter 7. Let's continue with our My Website project. Open your terminal and navigate to your My Website directory. CD path to My Website. Run Git status after a clean commit. If you just made your first commit in the previous chapter, running Git status should show Git status. On branch main. Nothing to commit, working tree clean. This is the ideal state. All your changes are committed, and your working directory perfectly matches the last committed snapshot. Make some changes. Let's modify our index.html file and create a new file. Modify index.html. Add a new paragraph below the existing one. Deocytyp HTML. HTML lang equals n. Head, meta charset equals UTF-8. Meta name equals viewport, content equals, width equals device width. Initial scale equals 1.0. Title my first website title. Head, body, h1 hello from Git, /h1. P this is my first version controlled website P. P welcome to new paragraph /P, added this line. Body, HTML, create a new file. Create a file named style CSS in the same directory with some content. Body, font family, Arial sans serif, background color, F4, F4, F4. Run git status again. Git status. This time, the output will reflect your changes. On branch main. Changes not staged for commit. Use git add file to update what will be committed. Use git restore file to discard changes in working directory. Modified. Index.html. Untracked files. Use git add file to include in what will be committed. Style CSS. No changes added to commit. Use git add and or git commit a. Git clearly categorizes the files. Index.html is listed under changes not staged for commit, meaning you've modified it since the last commit, but the changes aren't yet in the staging area. Style CSS is listed under untracked files, meaning it's a new file that Git hasn't seen before and isn't currently tracking. As you can see, Git status is your constant feedback mechanism, guiding you on what needs to be done. Staging changes, git add. The git add command is used to move changes from your working directory into the staging area. Remember from Chapter 2, the staging area is where you meticulously prepare the exact snapshot you intend to commit. Using our previous example, stage a specific file. Let's say you want to commit the index.html changes first, but not style CSS yet. Git add index.html. Check status after staging index.html. Git status. Output on branch main. Changes to be committed. Use git restore staged file to unstage. Modified index.html. Untracked files. Use git add file to include in what will be committed. Style CSS. Now, index.html is under changes to be committed, ready for the next snapshot. Style CSS remains untracked. Stage all new and modified files, shortcut. If you want to stage all modified, not deleted, and untracked files in your current directory and its subdirectories, you can use git add. Caution: be careful with git add. In a large project, as it might stage changes you're not ready to commit or files you didn't intend to track. It's often better to stage files individually or by specific groups. Check status after staging style CSS, e.g., using git add. After the previous step, git status. Output on branch main. Changes to be committed. Use git restore staged file to unstage. Modified index.html. New file, style CSS. Now both files are in the staging area. Viewing differences, git diff. Before committing, it's a good practice to review your changes. The git diff command allows you to see the exact modifications you've made. View changes in your working directory, not yet staged. First, let's unstage style CSS to demonstrate git diff on a modified but not staged file. We'll learn more about git restore in Chapter 8. Git restore staged style CSS. Now style CSS is back to untracked files. Let's also modify index.html again to add another line, so it has changes both staged and not staged. Previous content, P welcome to new paragraph /P. P this is yet another new line P, added this line. Body, HTML. Now index.html has staged changes, the first new paragraph, and unstaged changes, the second new paragraph. To see the differences between your working directory and the staging area, i.e., what you've changed since the last git add for a particular file. Git diff index.html. The output will show the additional line you just added to index.html, prefixed with a plus. View staged changes. To see the changes currently in your staging area, i.e., what will go into your next commit. Git diff staged. # for a specific staged file. Git diff staged index.html. This will show the first new paragraph you added to index.html when you initially ran git add index.html. Git diff's output uses a standard diff format. Lines prefixed with plus are additions and are deletions. Untouched lines may be shown for context. Committing changes, git commit. The git commit command takes the snapshot currently in your staging area and saves it permanently into your repository's history as a new commit object. This is a critical point in your workflow. Stage all current changes. Ensure both index.html, all its changes, and style CSS are staged. Git add. Hash or git add index.html, style CSS. Git status hash verify both are listed under changes to be committed. Commit with a message. As we saw in Chapter 3, the M flag allows for a direct, single-line message. Git commit M, add basic styling and extend homepage content. This is simple for small, clear changes. Writing good commit messages. A good commit message is vital for maintaining a clear and understandable project history. It helps you, your team, and future contributors understand why a particular change was made. Summary line, 50 to 72 chars. Start with a concise, imperative summary, e.g., add feature X. Fix bug Y, not added feature X. This line describes what the commit does. Blank line, follow the summary with a blank line. Detailed body optional, provide more context, explaining the why behind the change, what problem it solves, special considerations, or design decisions. Wrap lines at about 72 characters for readability by default. If your message requires multiple lines, omit the M flag. Git will then open your configured text editor, or Vim by default, for you to compose the message. Git commit. In the editor, type your summary on the first line. Leave a blank line. Type your detailed body. Save and close the editor, e.g. in Vim, type WQ and press enter. Example of a good commit message, feat. Add user authentication system. This commit introduces a new user authentication system, leveraging OAuth 2.0. Users can now sign up, log in, and manage their profiles. The system includes user registration endpoint, login and logout functionality, password hashing using bcrypt, session management via JWTs, addresses security concerns raised in issue 123. Viewing commit history, git log. The git log command displays your repository's commit history. It shows commits in reverse chronological order, newest first, by default. Git log. You will see output for each commit, including its SHA1 hash, author, date, and commit message, both summary and body. Git log has many useful options for filtering and formatting. Git log one line shows each commit on a single line with a shortened SHA1 hash and the summary. Great for a quick overview. Git log one line. Hash example. Hash 266 AW57 head main. Add basic styling and extend homepage content. Hash B1 A to C 3D initial commit of index.html. Git log graph shows a text-based graphical representation of the commit history, useful for visualizing branches and merges. Git log one-line graph combines the two for a compact graphical view. Git log one-line graph. Git log P or Git log patch shows the full diff for each commit, displaying exactly what changes were introduced in each snapshot. This can be very verbose. Git log author equals your name. Filters commits by author. Git log grep keyword filters commits whose messages contain a specific keyword. Git log n number shows the last number of commits. E.g., git log n5 shows the last 5 commits. Git log file name shows only the commits that affected a specific file. E.g., git log index.html. Press Q to exit the git log view if it opens in a pager, ignoring unwanted files. Git ignore explained. In almost every project, there are files you don't want Git to track. These might include build artifacts, files generated by your compiler, e.g. class files, O files, log files, application logs, debug logs, dependencies, folders containing installed packages, e.g. node modules / and node.js, vendor in PHP. Sensitive information, configuration files with API keys or passwords. IDE editor configuration files, files specific to your development environment, e.g., IDEA for IntelliJ, VSCode / for VSCode. Temporary files, OS-generated files like DSStore, macOS, or ThumbsDB, Windows. If you don't tell Git to ignore these files, they will constantly appear as untracked files when you run git status, cluttering your output and making it easy to accidentally commit them. Git uses a special file named git ignore to specify patterns of files and directories that it should ignore. Create a git ignore file In the root of your My Website project, create a new file named gitignore. Important. The file name starts with a dot, making it a hidden file on Unix-like systems. Touch gitignore hash on Linux Mac OS. Hash or create it using your text editor. Add patterns to gitignore. Open the gitignore file with your text editor and add patterns on separate lines. Let's say our My Website project will involve some Node.js development, and we generate some temporary files. Hash ignore Node.js dependency directory. Node module / hash ignore common OS files. DS store. thumbsdb. Hash ignore log files. Logs. Hash ignore temporary or generated files. TMP. Dist hash ignore a specific directory at the root. Rules for gitignore patterns. At the end indicates a directory. Logs ignores the logs directory. No leading matches files or directories anywhere in the repository. Log ignores all files ending with log wherever they are. Leading matches directories or files only at the root level. Dist ignores dist only if it's in the root. Subdir / dist / would still be tracked. Hash comments negates a pattern. If you ignore a directory but want to include a specific file within it. Logs important log. Wildcard for 0 or more characters. Wildcard for a single character. Test gitignore. Create some of the files you just listed in your gitignore file within your project. Hash create the node modules directory. mkdir node modules. Touch node modules / library.js. Hash create a log file. Touch app log. Hash create a temporary file. Touch temp.tmp. Now run git status. You should see only gitignore as an untracked file since you just created it, and none of the files you added within node modules / applog or temp.tmp should show up. Git status. On branch main. Untracked files. Use git add file to include in what will be committed. Gitignore. Nothing added to commit but untracked files present. Use git add and or git commit a. This confirms Git is successfully ignoring those files. Commit gitignore *. It's good practice to commit your gitignore file so that everyone collaborating on the project automatically uses the same ignore rules. Git add gitignore. Git commit m add gitignore file to exclude common project files. Summary and next steps. You've now mastered the essential commands for your daily Git workflow. Git status, your go-to for seeing the state of your project. Git add, for staging changes, carefully selecting what goes into your next commit. Git diff, for reviewing modifications before you commit them. Git commit, for saving your staged changes as a permanent snapshot in history, along with a meaningful message. Git log, for exploring your project's commit history. Gitignore, for telling Git which files and directories to ignore. These commands form the backbone of any project you work on. As you grow more comfortable, you'll naturally fall into a rhythm of making small, cohesive changes, staging them, reviewing them, and committing them frequently with clear messages. The next chapter will introduce one of Git's most distinguishing features: branching. Branches are fundamental to collaborative development and enable flexible workflows that would be cumbersome or impossible with other version control systems. Chapter 5, Branches, the backbone of collaborative development. Introduction, Parallel universes of development. In our journey so far, we've treated our main branch as a single, linear timeline of commits. You've made changes, staged them, and committed them, moving the main branch pointer forward in a straight line. This is great for individual development, but what happens when you need to introduce a new, potentially unstable feature, or fix a critical bug without disrupting the ongoing development of other features? What if multiple people need to work on different parts of the project simultaneously without stepping on each other's toes? This is where Git's branching capabilities truly shine. Branches are arguably Git's most powerful feature, enabling an incredibly flexible, collaborative, and nonlinear development workflow. They allow you to diverge from the main line of development, work in isolation on a new feature or bug fix, and then seamlessly integrate those changes back into the main project when they are ready. Think of a branch as a lightweight, independent line of development. When you create a branch, you're essentially creating a new parallel universe where you can make changes without affecting the existing code. What are branches and why are they fundamental to Git? As briefly mentioned in Chapter 2, A branch in Git is simply a movable pointer to a specific commit. It is not a separate copy of your code. When you make a new commit, the branch pointer automatically moves forward to point to this new commit, essentially creating a new tip of that branch. Let's visualize this. Imagine your commit history looks like this, where C0, C1, C2 are commits, and main is a pointer to the C2 commit. C0, C1, C2, main. When you make a new commit, C3, Git does a few things. It creates a new commit object, C3, that points back to C2, its parent. It moves the main pointer to C3. The history now looks like this: C0, C1, C2, C3, main. Now, let's say you want to work on a new feature without affecting main. You create a new branch, let's call it feature X initially. This new branch pointer will point to the same commit that main is currently pointing to C3. C0, C1, C2, C3, main, feature X. If you then switch to feature X and make some new commits, C4, C5, only the feature X pointer moves forward. The main pointer stays where it was: C4, C5, feature X, C0, C1, C2, C3, main. This clearly shows how feature X has diverged from main. You can work on feature X without worrying about destabilizing main, because main hasn't received any of these new commits yet. When feature X is ready, you can then choose to integrate its changes back into main, a process called merging, which we'll cover in the next chapter. This mechanism makes branching in Git incredibly fast and lightweight. Because branches are just pointers, creating, switching between, and deleting them takes virtually no time or disk space. This encourages developers to use branches frequently and liberally, leading to more organized and less risky development practices. Creating, listing, and deleting branches. Git branch. The git branch command is your primary tool for managing branches. Listing branches. To see all local branches in your repository, run git branch. Git branch. Output. Main. The asterisk indicates your currently checked out branch, the branch you are actively working on, and where head is pointing. Creating a new branch. To create a new branch, simply provide a name. Git branch feature user profile. This command creates the branch pointer, but it does not switch you to that branch. Your head, and thus your working directory, is still associated with main. Run git branch again to confirm the new branch exists. Git branch. Main. Feature user profile. Renaming a branch. If you need to rename the current branch, git branch new name. Or to rename a specific branch, not necessarily the current one, git branch old name new name. For example, git branch feature user profile feature auth system. Deleting a branch. Once a feature branch has been fully merged into your main branch and is no longer needed, it's good practice to delete it to keep your branch list clean. Git branch defeature user profile. The D or delete flag is a safe delete. Git will only allow you to delete the branch if it has been fully merged into your current head, i.e., its changes are incorporated elsewhere. If you try to delete a branch that contains unmerged changes, Git will warn you and refuse to delete it. To force delete a branch, use with caution. This will delete the branch regardless of whether its changes are merged or not, potentially losing work if you're not careful. Git branch defeature user profile #D for force delete. Switching between branches, git checkout and git switch. To work on a different branch, you need to check out that branch. When you check out a branch, Git does two main things. It moves your head pointer to point to that branch. It updates your working directory to reflect the snapshot that the target branch is pointing to. This means files might appear, disappear, or change content to match that branch's history. Historically, git checkout was the command used for many operations, including switching branches, restoring files, and more. Git version 2.23 introduced git switch and git restore to make these operations clearer and safer. While git checkout still works for switching branches, it's generally recommended to use git switch for this purpose. Switching to an existing branch. Let's switch to our newly created feature user profile branch. Git switch feature user profile. Output, switch to branch, feature user profile. Now git branch will show. Git branch. Main. Feature user profile. At this point, your feature user profile branch and main branch point to the same commit. Creating and switching to a new branch, shortcut. This is a very common action. You can combine git branch and git switch into one command. Git switch, see new feature branch. This command will create new feature branch and immediately switch your head to it. Using git checkout, be new feature branch achieves the same with the older command. Understanding head. As discussed in Chapter 2, head is the single most important pointer in Git. It's essentially the current commit that you are working on. When head points to a branch, e.g. head main, it means your working directory reflects the state of that branch's latest commit, and any new commits you make will advance that branch. This is the normal state of affairs. When head points directly to a commit, e.g. head B1A to C3D, you are in a detached head state. This means your working directory still reflects that commit, but any new commits you make will not be associated with a branch. This can lead to lost commits if you're not careful, as they might become unreachable once you switch back to a branch. The detached head state happens when you check out a specific commit hash or a tag. We'll explore using this state more safely in advanced scenarios, e.g., debugging with Git bisect. Basic branching strategy for feature development. A common and effective branching strategy is the feature branch workflow. This is a simple, flexible approach particularly suitable for single-team projects. Start from main or a develop branch. Always begin new features or bug fixes from a stable, known good baseline. Git switch main. Git pull hash, more on this in Chapter 7, but generally a good idea to update. Create a new feature branch, give it a descriptive name. Git switch C feature add dark mode. Develop on the feature branch. Make your changes, git add and git commit frequently. These commits are isolated to your feature branch and do not affect main. Hash edit files, e.g. style CSS, script.js. Git add. Git commit m, implement dark mode toggle. Hash more edits. Git add, git commit m, refine dark mode color palette. Your history now looks like C4, C5, feature add dark mode. C0, C1, C2, C3 main. Finish the feature. Once the feature is complete, tested, and reviewed, often via a pull request or merge request on platforms like GitHub, which we'll cover later, you integrate it back into main. The next chapter will cover this process of merging. Clean up. After integration, delete the feature branch. Git switch main hash first, switch back to the branch you're merging into. Git merge feature add dark mode hash. We'll learn this in Chapter 6. Git branch defeature add dark mode. This simple strategy ensures that your main branch always remains stable and deployable. New development happens in isolation, minimizing risks. Multiple developers can work concurrently without interfering with each other's work directly. Summary and looking ahead. Branches are the foundation of collaborative and robust development in Git. By understanding that a branch is simply a movable pointer to a commit, you unlock a world of agile workflows. You've learned how to list existing branches, Git branch. Create new branches, Git branch name or Git switch C name. Switch between branches, Git switch name. Delete branches, Git branch D name or Git branch D name. Appreciate the role of head as your current working location. Implement a basic feature branching strategy. The next crucial step is to learn how to integrate changes from one branch into another, the process of merging. This is where multiple parallel universes of development converge, and where you'll also learn to handle conflicts that inevitably arise when different lines of work touch the same code. Chapter 6. Merging and Resolving Conflicts. Bringing Work Together. Introduction. The Convergence of Parallel Universes. In the last chapter, we explored the incredible flexibility of Git's branching model. You learned how to create separate universes of development, allowing you to work on new features or bug fixes in isolation without affecting the main codebase. But what happens when your isolated work is complete, tested, and ready to be integrated into the main project? This is where merging comes in. Merging is the process of combining the history of two or more branches into a single, unified history. It's how you bring the changes from your feature branch back into your main branch, or integrate changes from a remote branch into your local development. While the concept is simple, the reality can sometimes involve merge conflicts, situations where Git can't automatically figure out how to combine changes from different branches. This chapter will demystify the merging process and provide a clear step-by-step guide to resolving conflicts. The concept of merging in Git. When you merge one branch into another, Git attempts to combine the changes from the source branch, the one you're merging from, into the target branch, the one you're currently on. Git determines the best way to do this by looking at the common ancestor commit of the two branches, and then applying the changes introduced by each diverging branch. Git typically performs two main types of merges. Fast-forward merges. This happens when the target branch, e.g., main, has not diverged from the source branch, e.g., feature X, since the feature branch was created. In other words, the main branch is a direct ancestor of the feature X branch. Git simply moves the pointer of the target branch forward to the latest commit of the source branch. No new merge commit is created. This history remains linear. Analogy: imagine pushing a shopping cart down a straight aisle. You're just moving it forward to catch up with where the other cart is. Three-way merges. This occurs when both the target branch and the source branch have diverged since their common ancestor. Git needs to combine changes from both lines of development. Git identifies the common ancestor commit, then looks at the changes on each branch since that ancestor. It tries to apply both sets of changes. A new merge commit is created, which has two or more parent commits, the latest commit of the target branch and the latest commit of the source branch. This keeps the history of both branches and shows explicitly where they were combined. Analogy: you're assembling two different Lego models, but they both started with the same base set. You need to combine the unique additions from both models onto a new, larger base. Performing a merge, git merge. Let's illustrate merging with an example. Assume you have main and a feature contact form branch. Start on main and create a feature branch, git switch main. #ensure main is up to date, though not strictly necessary for this example. #git pull, git switch c feature contact form. Make some commits on feature contact form. Create a new file, contact.html. Contact.html. deocytoip HTML. HTML lang equals n. Head, meta charset equals UTF-8. Title contact us title. Head, body, h1 contact form h1. P this is where the contact form will go p. Body, HTML. Git add contact HTML. Git commit m, add basic contact page. History, main is at C3, feature contact form is at C4. C4 feature contact form. C0, C1, C2, C3 main. Switch back to main and make a commit there to force a three-way merge. For a three-way merge, main needs to have moved forward. Let's add a products.html file to main. Git switch main. Create products.html. Products.html. deocytoip HTML. HTML lang equals n. Head, meta charset equals UTF-8. Title our products title. Head, body, h1 our products h1. P check out our amazing products, /p. Body, HTML. Git add products HTML. Git commit m, add products page to main. Now history looks like this. Main is at C6, feature contact form is at C4, C3 is the common ancestor. C4, feature contact form. C0, C1, C2, C3, C6 main. Perform the merge. To integrate the feature contact form changes into main, you must be on the main branch. Git switch main. Git merge feature contact form. Git will attempt the merge. If successful, for our example, it will create a merge commit, C7, and might provide a default commit message, which you can accept or edit. Merge branch feature contact form. Please enter the commit message for your changes. Line starting. With hash will be ignored and an empty message aborts the commit. After saving the merge message, e.g. in vim type wq, Git will confirm the merge. Merge made by the recursive strategy. Contact HTML 11 plus 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 plus. One file changed, 11 insertions, plus. Create mode 100,644, contact HTML. The history now looks like this. Main is at C7. C7 has two parents, C6, the tip of main before the merge, and C4, the tip of feature contact form. C4, //, C0, C1, C2, C3, C6, C7 main. This diamond shape in the history graph clearly shows the integration point. Understanding merge conflicts, when work collides. A merge conflict occurs when Git cannot automatically resolve differences between two branches. This typically happens when changes to the same line. both branches modify the same lines in the same file. Changes to different parts of the same line. For example, one branch adds text at the beginning of a line, and another adds text at the end. Renaming, deleting. One branch renames or deletes a file that the other branch has modified. When a conflict occurs, Git will pause the merge process and tell you which files have conflicts. Your job is to manually resolve these conflicts. Let's create a conflict scenario. Redo previous steps to reach the divergent state. Using Git reset hard C6 on main and recreate feature contact form from C3 and add contact HTML with C4 as before. History before conflict scenario setup. C4 feature contact form. C0, C1, C2, C3, C6 main. Introduce conflicting changes. On main, currently at C6, edit index HTML to add a footer. Previous content. P. This is yet another new line P. Body. Footer. P. Copyright 2023. All rights reserved P. Footer. HTML. Git add index HTML. Git commit M. Add copyright footer to index HTML. New commit C8 on main. On feature contact form, still at C4. Switch to feature contact form and also edit index HTML at the same location to add a header. Git switch feature contact form. Edit index HTML. Index HTML. Deocytoip HTML. HTML lang equals n. Head. Meta charset equals UTF-8. Meta name equals viewport. Content equals width equals device width. Initial scale equals 1.0. Title my first website title. Head. Header. H1 welcome to our site, /H1. Header. Body. H1 hello from Git, /H1. P. This is my first version controlled website P. P. Welcome to a new paragraph, /P. Body. HTML. Git add index HTML. Git commit M. Add welcome header to index HTML. New commit C9 on feature contact form. Current history. C4 C9, feature contact form. C0, C1, C2, C3, C6, C8 main. Attempt the merge and encounter conflict. Git switch main. Git merge feature contact form. Git will stop and output something like auto-merging index HTML. Conflict content. Merge conflict in index HTML. Automatic merge failed. Fix conflicts and then commit the result. And if you run git status on branch main, you have unmerged paths. Fix conflicts and run git commit. Use git merge abort to abort the merge. Unmerged paths, use git add file to mark resolution. Both modified, index HTML. No changes added to commit, use git add and or git commit A. The index HTML file is now in a conflicted state. Resolving conflicts step by step. When Git reports a conflict, it modifies the conflicted file by adding special conflict markers. These markers show you where the conflicting changes are. Inside index HTML, after conflict, open index HTML in your text editor. You'll see something like this. Index HTML. Deocytoip HTML. HTML lang equals n. Head. Meta charset equals UTF-8. Meta name equals viewport. Content equals width equals device width. Initial scale equals 1.0. Title my first website title. Head. Head. Footer. P. Copyright 2023. All rights reserved P. Footer. Header. H1 welcome to our site, /H1. Header. Feature contact form. Body. H1 hello from Git, /H1. P. This is my first version controlled website P. P. Welcome to a new paragraph, /P. Body. HTML. The conflict markers are. Head marks the beginning of the changes from your current branch. Head refers to main. Equals 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 separates the changes from the two branches. Feature contact form marks the end of the conflict section, showing the changes from the branch you're merging. Feature contact form. Your task is to edit index HTML to remove these markers and combine the conflicting lines in a way that makes sense for your project. You can choose to keep the changes from head main, to keep the changes from feature contact form, to combine both sets of changes, to discard both and write something completely new. For our example, let's say we want to keep both the header and the footer. We'll manually combine the code. Index HTML. Deocytoip HTML. HTML lang equals n. Head. Meta charset equals UTF-8. Meta name equals viewport. Content equals width equals device width. Initial scale equals 1.0. Title my first website title. Header, H1 welcome to our site, /H1. Header, body, H1 hello from Git, /H1. P this is my first version controlled website P. P welcome to a new paragraph, /P. Body, footer, P copyright 2023. All rights reserved P. Footer, HTML, save the file after editing. Using Git's merge tools, for more complex conflicts, especially across multiple files, using a visual merge tool can be invaluable. Git can be configured to launch a graphical diff merge tool when a conflict occurs. Many popular IDEs, like VS Code, IntelliJ, etc., have excellent built-in merge conflict resolution UIs. You can also configure external tools like kdiff3, meld, or beyond compare to launch your configured merge tool for conflicted files. Git merge a tool. This will open each conflicted file in your chosen tool, allowing you to visually accept parts from each side and save the result. After closing the merge tool for a file, Git will automatically stage the resolved version. Completing the merge. Mark the conflict as resolved. After manually editing the files and removing all conflict markers, you need to tell Git that you've resolved the conflict. Git add index.html hash stage the resolved file. If you used Git merge a tool, it usually stages the file automatically. Commit the merge. Once all conflicts are resolved and staged, you complete the merge by making a merge commit. Git commit. Git will automatically generate a merge commit message, e.g., merge branch feature contact form into main, which you can accept or modify. Save and close the editor. The merge is now complete, and the history reflects the common ancestor and the combined changes from both branches, leading to a new merge commit on main. Aborting a merge. If you get into a hopeless mess during a merge and want to start over, you can abort the merge operation. Git merge abort. This will revert the repository to the state it was in before you started the merge attempt. All changes from the merge attempt will be undone. Summary and next steps. Merging is a core operation in Git that allows you to integrate parallel lines of development. You've learned the difference between fast-forward merges, linear history, and three-way merges, new merge commit, preserving distinct histories. How to initiate a merge from your target branch using Git merge source branch. The concept of merge conflicts and why they occur. How to identify and manually resolve conflict markers, How to use Git status to guide your conflict resolution process. How to complete a conflicted merge by staging the resolved files and making a merge commit. How to abort a merge if things go wrong. Mastering merging and conflict resolution is a crucial skill for any Git user. It enables effective collaboration and the agile integration of new features. In the next chapter, we'll expand on this by introducing remote repositories, allowing you to share your work and collaborate with others across networks. Chapter 7, Remote Repositories, Collaborating Across the Globe. Introduction, Extending Your Reach. So far, we've focused on Git's local capabilities. Tracking changes, making commits, and managing branches all within your own computers, Git directory. This local power is a cornerstone of Git's distributed nature, enabling offline work and fast operations. However, the real magic of Git, especially in a team environment, comes alive when you start collaborating with others. This is where remote repositories enter the picture. A remote repository is simply another copy of your Git repository, hosted somewhere else, typically on a server. Platforms like GitHub, GitLab, and Bitbucket specialize in providing hosted remote repositories, along with powerful tools for collaboration, code review, and project management. This chapter will explain the role of remote repositories and guide you through the essential commands for interacting with them. Viewing and managing remotes, retrieving, fetching changes from them, downloading and merging, pulling, changes, and uploading, pushing your local work for others to see. The role of remote repositories, GitHub, GitLab, Bitbucket. Remote repositories serve several critical functions. Collaboration hub. They provide a central point where multiple developers can share their code and synchronize their work. Instead of passing files around, everyone pushes their changes to and pulls changes from the remote. Backup. Your work is backed up remotely. If your local machine crashes, your project history is safe on the remote server. Code review and CI/CD. Platforms like GitHub facilitate code reviews through pull requests or merge requests. Continuous integration, CI, and continuous deployment, CD, pipelines, automating testing and deployment processes. Open source contribution. Remote repositories, especially on platforms like GitHub, are the backbone of the open source world, allowing anyone to contribute to projects. When you git clone a repository, as we did in Chapter 3, Git automatically sets up a default remote connection named origin, pointing to the URL you cloned from. This origin is just a conventional name. You could name it anything you want, and you can have multiple remotes. Viewing and managing remotes, git remote. The git remote command helps you inspect and manage the connections to your remote repositories. Listing remotes. To see which remotes are configured for your repository, git remote. If you've cloned a repository, you'll typically see origin as the output. If you initialized a local repository and haven't connected it to a remote yet, this command will show nothing. Listing remotes with URLs. To see the URLs associated with each remote, use the v verbose flag, git remote v. Output example from a cloned repository. Origin https github.com/octocat/spoon-knifegit fetch. Origin https github.com/octocat/spoon-knifegit push. This shows that origin is configured for both fetching changes from the remote and pushing changes to the remote. Adding a remote. If you start a project locally with Git init and then decide to host it on a platform like GitHub, you'll need to add a remote. Scenario: you've created an empty new repository on GitHub or GitLab/Bitbucket. It will give you a URL like https github.com/your-username/my-website-git. Command: git remote add origin https github.com/your-username/my-website-git. This command adds a new remote connection, names it origin, and associates it with the provided URL. Removing a remote. If a remote URL changes or you no longer need a connection, git remote remove origin. Renaming a remote. Perhaps origin isn't descriptive enough or you want to change it. Git remote rename origin upstream. Now origin will be called upstream. Retrieving changes from a remote. Git fetch. Git fetch is your way of checking what's new on the remote without altering your local working copy. It downloads all the new data, commits, branches, and tags from the remote repository that you don't have yet, but it does not merge or modify your local branches. Think of it as quietly checking the mail, seeing what new letters have arrived, but not opening or sorting them yet. Git fetch origin. Output example from https github.com/octocat/spoon-knife. New branch main origin main. New branch development origin development. After a git fetch, Git has updated its knowledge of what's on the origin remote. Specifically, it updates your remote tracking branches, e.g., origin main, origin development. These are local copies of the branches on the remote, indicating the remote state at the last fetch. Your local main branch, however, remains untouched unless you explicitly merge the changes. You can then use git diff main origin main to see what changes are on the remote's main branch that you don't have locally. Downloading and merging changes. Git pull. Where git fetch downloads but doesn't integrate, git pull does both. It's essentially a convenience command that performs a git fetch followed by a git merge. When you run git pull, Git will fetch all changes from the remote repository. Merge the changes from the remote's tracked branch, e.g., origin main, into your current local branch, e.g., your local main branch. Warning: because git pull performs a merge, it can result in merge conflicts if your local changes overlap with changes on the remote. It's generally best practice to ensure your local working directory is clean or your changes are committed before performing a git pull. Git pull origin main. This command tells Git to pull changes from the main branch of the origin remote into your currently checked out local branch. If your current branch is main and it's set up to track origin main, you can often just use git pull. Git will automatically figure out which remote and branch to pull from. It's a good habit to git pull frequently, especially when working in a team, to keep your local repository synchronized with the latest changes from your teammates. Uploading local changes, git push. Once you've made changes locally and committed them, you'll want to share them with your team and the remote repository. This is done with Git push. Git push uploads your local commits to the specified remote repository and updates the remote's branch with your changes. Git push origin main. This command pushes all new commits from your local main branch to the main branch on the origin remote. First time push, setting upstream. The very first time you push a newly created local branch to a remote, Git might tell you that it doesn't know where to push. You'll typically see a suggestion like, fatal. The current branch name has no upstream branch. To push the current branch and set the remote as upstream, use Git push set upstream origin branch name. The set upstream, or U for short, flag tells Git to create a tracking relationship between your local branch and the remote branch. After this, subsequent Git push and Git pull commands for that branch won't require specifying the remote and branch names, e.g., Git push will suffice. Avoiding issues with Git push. Pushing divergent history. If the remote branch has new commits that you don't have locally, i.e., your local branch is behind the remote, and you haven't pulled or fetched and merged them, Git will refuse to push. It will tell you that the remote has work that you don't and suggest you pull first. This prevents you from accidentally overwriting someone else's work. Force pushing, Git push force or force with lease. This command overwrites the remote branch with your local branch, regardless of the remote's history. It should be used with extreme caution and only if you know what you're doing, as it can permanently erase others' work. Force with lease is a safer alternative that checks if the remote branch has been updated since you last pulled. Generally, avoid force pushing branches that other people are working on. Understanding origin and main master. Origin, this is the default alias Git gives to the remote repository you cloned from. It's just a convenient name for a URL. You can change it or add other remotes with different names if you need to fetch from multiple sources. Main master. This is the conventional name for the primary or default branch in a Git repository. It typically represents the stable, production-ready version of the code. New features are usually developed on separate branches and then merged into main when ready. Basic team collaboration workflow using remotes. Putting it all together, here's a common basic workflow for a team of developers using Git and a remote repository. Clone the repository. Git clone https github.com/your-org/your-project git. Once at the start of your project. Stay updated. Before starting new work, get the latest changes from the remote. Git switch main hash, make sure you are on your main branch. Git pull hash fetch and merge latest changes from origin main. Create a feature branch. Git switch C feature your awesome feature. Work and commit locally. Make changes, git add, and git commit frequently. Hash make changes, git add. Git commit M implement feature X. Share your work, push your feature branch. When your feature is stable or you want to back it up, push your local feature branch to the remote. Git push U origin feature your awesome feature hash first time for this branch. Hash subsequent pushes. Git push. Integrate, merge pull request. Once your feature is complete and reviewed, e.g., via a pull request or merge request on GitHub GitLab, it will be merged into the main branch on the remote. This is usually done through the web interface of the hosting platform. After the merge on the remote, you can safely delete your local and remote feature branches, as its history is now part of main. Loop back. Repeat from step 2 for your next task. This cycle of pulling updates, creating separate branches for new work, committing changes, pushing those changes, and integrating them through merges, often via pull requests, forms the backbone of modern collaborative software development with Git. Summary and looking ahead. Remote repositories are indispensable for collaborative development, offering backup, synchronization, and platforms for advanced workflows. You've gained an understanding of the crucial role of remotes and common hosting platforms, how to inspect and manage your remote connections, Git remote. The difference between Git fetch, download only, and Git pull, download and merge. How to share your local changes with others using Git push. The conventions of origin and main master. A fundamental team collaboration workflow using remotes and feature branches. You now have a solid command of Git's core functionalities, from local history management to distributed team collaboration. In the next chapter, we'll delve into fixing mistakes and rescuing your repository. Git's design makes it incredibly resilient, and you'll learn how to leverage that power to undo errors and navigate challenging situations. Chapter 8: Undoing Mistakes, Rescuing Your Repository. Introduction: The Git Safety Net. Even the most meticulous developer makes mistakes. You commit too early, realize you forgot a crucial change, accidentally delete a file, or introduce a bug and need to roll back. Such scenarios can be terrifying without a robust version control system. Git is designed to be incredibly forgiving. Almost nothing is truly lost in Git once it's committed, and even non-committed changes can often be recovered. Git's foundational principle of storing snapshots and its content-addressable nature act as a powerful safety net, allowing you to undo, rewind, and rewrite history carefully, without fear of permanent data loss. This chapter will introduce you to Git's undo capabilities, covering common recovery scenarios from small blunders to significant history rewrites. We'll explore Git restore, Git reset, Git revert, and the invaluable Git reflog. Common errors and why Git makes them recoverable. Imagine these common scenarios. Oh no, I deleted that file. You accidentally remove a file from your working directory. I added too much to the staging area. You ran git add, but didn't mean to include a specific file in the next commit. Forgot to add a change to my last commit. You committed, then immediately realized a minor fix was missing. That last commit has a typo in its message. A minor, embarrassing error in the commit history. This feature branch is a total mess. I need to go back to a clean state. Your experiment went wrong. That entire feature was a bad idea. How do I delete the last n commits? A more drastic rollback. Because Git tracks content, not just changes, and because its history is based on immutable commit objects uniquely identified by their SHA-1 hashes, it provides powerful mechanisms to return to any previous recorded state or to create new history that effectively undoes past actions. The key to Git's resilience is that commits are immutable. When you undo a commit, you're usually not deleting it. Rather, you're creating new history that either effectively reverses the original commit or moves your branch pointers to different commits, potentially making the old ones unreachable, but still recoverable for a time. Undoing changes in the working directory. Git restore. The git restore command, introduced in Git 2.23, is explicitly designed for managing changes in your working directory and staging area, providing a clearer way to undo modifications. Let's use our My Website project. Make changes, modify index.html, e.g., delete a paragraph, add some gibberish. #modify index.html. Check status. Git status. On branch main. Changes not staged for commit. Use git add file to update what will be committed. Use git restore file to discard changes in working directory. Modified index.html. Discard changes in working directory. If you decide you don't want those modifications and want to revert index.html to its last committed state or last staged state, git restore index.html. This command effectively undoes any modifications you've made to index.html since it was last committed or staged, bringing it back to the version in your staging area, if it was staged, or your last commit, if it wasn't. Important: Git restore file will discard your uncommitted, unstaged changes permanently. Be sure you don't need those changes before running this. Unstaging files. Git restore staged. Sometimes you git add a file and then realize you don't want to include it in the next commit. Git restore staged helps here. Modify and stage. Modify index.html again. #modify index.html. Git add index.html. Now index.html is in the staging area. Check status. Git status. On branch main. Changes to be committed. Use git restore staged file to unstage. Modified index.html. Unstage the file. Git restore staged index.html. This command moves the file out of the staging area, back into the modified, unstaged state in your working directory. The changes are still there, but they are no longer marked for the next commit. Check status again. Git status. On branch main. Changes not staged for commit. Use git add file to update what will be committed. Use git restore file to discard changes in working directory. Modified index.html. No changes added to commit. Use git add and or git commit a. Now index.html is again under Changes Not Staged for Commit, allowing you to git add it later or git restore it to discard changes. This is typically used when you accidentally stage a file you don't want to commit yet. Rewriting commit history carefully. Git reset. Git reset is a powerful and versatile command for undoing commits by moving your branch pointers. It's often used to discard recent local commits or to unstage changes. However, it can alter history, so use it with understanding. Git reset affects two things, which commit the current branch pointer points to: the state of the staging area and working directory. It has three main modes: soft, mixed, default, and hard. Let's assume your log looks like this: a BCD head main, where D is your latest commit. Git reset hard commit. Discarding commits and changes, dangerous. This is the most aggressive form of reset. It moves your current branch pointer to commit, resets the staging area to match commit, resets your working directory to match commit. All uncommitted changes and all commits after the target commit are permanently removed from your working directory. Scenario: you've made some commits, C, D, on your local main branch, but they're terrible, and you want to completely discard them and revert to the state of commit B. Git reset. Hard BSHA hash replace BSHA with the actual SHA, one of commit B. Hash or to go back one commit. Git reset, hard head ~1. History becomes a B head main. Your working directory will now reflect the exact state of commit B when to use, only on your local, unpushed commits that no one else has. Never on shared history, as it rewrites history and will cause massive problems for collaborators. Use it for personal experimentation or to thoroughly clean up recent bad commits before pushing. Git reset mixed commit, uncommitting and unstaging, default. This is the default mode, so git reset commit is equivalent to git reset mixed commit. It moves your current branch pointer to commit, resets the staging area to match commit, does not touch your working directory. All changes from the discarded commits, C, D, are now unstaged modifications in your files. Scenario: you committed some changes, C, D, that were okay, but you'd prefer to combine them differently or amend them. You want those changes to be in your working directory, but not committed or staged. You want to go back to commit B. Git reset head hash go back one commit, i.e. to C. History becomes a BC head main, but the content of commit D is now unstaged in your working directory. If you instead do git reset head ~2, it goes back to B, and the combined changes from C and D are unstaged. When to use: most commonly used to uncommit recent local commits while preserving the changes in your working tree, allowing you to restage and recommit them with a new structure or message. Git reset soft commit, uncommitting, preserving staged changes. This is the least aggressive form. It moves your current branch pointer to commit, does not touch the staging area. All changes from the discarded commits C, D remain in the staging area, does not touch your working directory. Scenario: you just made a commit D and realized its message is wrong or you forgot a small detail. You want to undo the commit itself, but keep all the changes staged, ready for an amend or a fresh commit. You want to go back to commit C, but keep D's changes staged. Git reset soft head ~1. History becomes a BC head main. The changes that were in commit D are now in your staging area, ready for you to git commit amend, to update the last commit, or simply git commit to create a new one. When to use: primarily used to modify the last commit you made, using git commit amend after git reset soft head combined with some new changes. Creating new history to undo. Git revert. Unlike git reset, which moves or rewrites existing commit history, git revert creates a new commit that undoes the changes introduced by a previous commit. This is generally the safest way to undo changes, especially on branches that have been pushed to a remote and shared with others. Why git revert is safer for shared history? It does not rewrite history. It adds a new commit, preserving the original commits. It's non-destructive. The original commit remains in the history. It avoids problems with pushed history, as everyone still has the original commits, and they simply pull your new revert commit. Scenario: commit C introduced a bug or a feature that's no longer needed. You want to undo commit C, but you've already pushed C to the remote. A BCD head main. To undo the changes made in commit C, git revert CSHA, hash replace CSHA with the actual SHA, one of commit C. Git will create a new commit. Let's call it E, that contains reverse patches of the changes introduced in C. You'll typically be prompted to confirm a commit message like revert bug fix for X feature. Save and exit the editor. History becomes a BCDE head main. Commit E effectively cancels out the changes from commit C. The history clearly shows both C, the original change, and E, the undoing of C, which can be valuable for auditing. Important: if you revert a commit that was merged into your branch, you may need to revert the revert later if you remerge the original branch. This can get complex. Use git revert for specific commits that perhaps introduced bugs or bad features. It's not usually used to delete a series of commits like git reset hard. The safety net. Git reflog. Git reflog is your unsung hero, your ultimate safety net, and the time machine you'll turn to when you think all hope is lost. Git keeps a record of every single time your head pointer has moved, for a certain period, usually 30 or 90 days, depending on Git's garbage collection settings. This record is called the reflog reference log. Every time you git commit, git mert, git pull, git rebase, git reset, git switch checkout, or any other operation that moves head, an entry is added to your reflog. Scenario: you accidentally ran git reset, hard head -5 and lost 5 commits. Panic sets in, run git reflog, Output might look like A1 B2C 3D head at 0, reset. Moving to head -5, E4 F5 G6H head at 1, commit, add another feature. I7 J8 K9 L head at 2, commit, fix minor bug. Z0 Y9 X8 W head at 10, checkout, moving from feature branch to main. The head at 10 syntax refers to the state of your head n steps ago. The SHA1 hash is the commit your head was at. Find the commit you want to go back to. In the reflog output, locate the state before your accidental reset. For instance, if E4 F5 G6H was the commit you wanted to return to, you can see it in the reflog. Restore your branch. Once you have the SHA, one of the desired commit, e.g., E4 F5 G6H, you can force your branch to point back to it using git reset hard. Git reset hard E4 F5 G6H. Your main branch and your working directory will now be back to exactly where it was before your mistake. Key takeaway: git reflog shows you where your head has been. Even if a commit is no longer referenced by any branch, it stays in the reflog for a period, giving you a chance to recover it. It's truly your last line of defense against data loss in Git. Summary and going further. Git's powerful undo capabilities provide immense flexibility and safety. You've learned about git restore file for discarding unstaged changes in your working directory. Git restore staged file for unstaging files that were git added. Git reset soft commit to uncommit keeping changes staged. Git reset mixed commit default to uncommit and unstage keeping changes in the working directory. Git reset hard commit to uncommit, unstage, and discard all changes use with extreme caution. Git revert commit to create a new commit that undoes a previous commit safe for shared history. Git reflog, your ultimate safety net for recovering lost commits or states. With these commands under your belt, you can confidently experiment and modify your repository's history, knowing that Git has powerful recovery mechanisms at your disposal. The next chapter will delve into Git rebase, a powerful feature that allows for cleaner, linear history, but also comes with its own set of risks and best practices. Chapter 9, The Power of Rebase. Rewriting history carefully. Introduction, Reshaping your history. In Chapter 6, you learned about Git merge, our primary tool for integrating changes from one branch into another. Merging is about combining histories, resulting in a nonlinear history with merge commits that show where development lines converged. While this accurately reflects the history, it can sometimes lead to a messy commit graph, especially with many short-lived feature branches. Enter Git rebase. Rebase is another way to integrate changes from one branch into another, but instead of creating a merge commit, it attempts to rewrite the commit history of your current branch as if your commits were created directly on top of the target branch. This results in a cleaner, linear history that can be easier to read and understand. However, with this power comes great responsibility. Git rebase rewrites history, and this has significant implications, especially when dealing with shared branches. What Git rebase does and how it differs from Git mer. Let's illustrate with a common scenario. Imagine your main branch has progressed, and you have a feature X branch that you started a while ago. Initial state. A BC main. \DE feature X. Here, C is the common ancestor where feature X branched off. Main has progressed with commit C feature X has commits D and E git merge scenario. If you switch to main and run git merge feature X, Git finds the common ancestor, C, takes the changes from D and E, and combines them with main's history from C to create a new merge commit M on main. A BCFM main. \DE feature X. The history clearly shows that D and E came from a separate branch. Git rebase scenario. Now, let's go back to the initial state and perform a rebase. You are on feature X and you want to rebase it onto main. Git switch feature X. Git rebase main. What Git rebase main does internally. Git finds the common ancestor of feature X and main, which is C. It takes all the commits unique to feature X, since that common ancestor commits D and E. It temporarily rewinds feature X to the point where it diverged from main back to C. It moves your head to the tip of the main branch, commit F. It then reapplies those unique commits, D and E, one by one on top of F because they are reapplied. They become new commits. D and E have new SHA1 hashes, although their content is the same. After git rebase main, a BCF main. \DE feature X. Notice how the feature X branch now appears to have started directly from main's latest commit F. The history of feature X is rewritten, making it look like a linear progression from main. Key differences. History. Merge preserves full history, including merge commits, resulting in a nonlinear graph. Rebase rewrites history, creating a linear graph without merge commits. Commit hashes. Merge preserves original commit hashes. Rebase creates new commit hashes for the reapplied commits, D and E. Safety. Merge is generally safer for shared history. Rebase on shared history is risky. When to use rebase and when not to. When to use rebase. To keep your feature branch up to date with main before merging. This is the most common and recommended use case. Before you merge your feature X branch into main, you might rebase feature X onto a clean main branch. This pulls in all the latest changes from main into your feature branch, resolving any conflicts within your feature branch, making the final merge into main a simple fast forward. If main hasn't had new commits since your rebase, or a merge with minimal conflicts if main has progressed further. Git switch feature X. Git rebase main. Hash resolve any conflicts if they occur during the rebase. Hash continue the rebase. Git rebase continue. Hash after rebase, switch to main and merge. Git switch main. Git merge feature X. Hash this will likely be a fast forward merge. To squash or combine commits on a local branch, interactive rebase. For internal development, you might have many small commits on a feature branch. Before merging, you might want to combine them into fewer, more meaningful commits. Interactive rebase, Git rebase I, is perfect for this, see below. To clean up commit messages or reorder commits on a local branch. Again, using interactive rebase on an unpushed branch. When not to use rebase, never rebase branches that have already been pushed to a public shared remote and others have pulled them. This is the golden rule of rebasing. Because rebase rewrites history, changing commit SHA1 hashes. If you rebase a branch that someone else has already pulled, their history and your history will diverge. When they try to push or pull, Git will see fundamentally different histories for the same commits, leading to confusion, forced pushes, and a lot of headaches. Rebase only branches that exist locally, or that you have exclusive control over, e.g., your own remote feature branch that no one else has pulled yet. Performing a simple rebase. Let's assume we have our main branch with C7 and a feature refactor branch created from C3. C4, feature/refactor. Original. C0, C1, C2, C3, C6, C7 main. And now feature refactor has a new commit C8 and C9. C4, C8, C9, feature refactor. C0, C1, C2, C3, C6, C7 main. We want to update feature refactor to be based on C7. Ensure main is up to date. Git switch main. Git pull hash get latest changes from remote main. Switch to your feature branch. Git switch feature refactor. Rebase onto main. Git rebase main. Git will tell you what it's doing, possibly leading to conflicts covered next. Upon success, your history will look like this: C4, C8, C9, feature refactor. C0, C1, C2, C3, C6, C7 main. Resolving conflicts during rebase. Just like merges, rebases can encounter conflicts. The conflict resolution process is similar, but the context is different. During a regular merge, you resolve conflicts once, and then you commit. During a rebase, Git applies each commit from your feature branch one by one on top of the target branch. If a conflict occurs during the application of any of these commits, Git will pause the rebase. Steps to resolve rebase conflicts. Git pauses and informs you: conflict, content, merge conflict in file. Error. Could not apply some commit hash. Commit message. Resolve all conflicts manually. Mark them as resolved with git add/rm conflicted file, then run git rebase continue. Examine conflict markers. Open the conflicted files in your editor. They will contain == markers, but head will refer to the state of the commit being reapplied, and the other side will be the target branch. Resolve conflicts. Edit the files to combine the changes as desired. Stage resolved files. Git add conflicted file.js. Continue the rebase. Git rebase continue. Git will then try to apply the next commit. This process repeats until all commits from your target branch have been successfully reapplied. Options during rebase. Git rebase abort. To completely stop the rebase and return your branch to its state before you started the rebase. Git rebase skip. To skip the current conflicting commit entirely. Use with caution, as it will mean the changes in that commit are lost. Interactive rebase. Squashing, editing, reordering commits. Git rebase interactive rebase is an incredibly powerful tool for cleaning up your local commit history before pushing. It allows you to squash multiple small commits into a single, cohesive commit, edit, amend existing commits to change their messages or add, remove changes, reorder commits, drop, delete commits, split a single commit into multiple commits. How to use Git rebase. Identify the target commit. You need to tell Git how far back to go. This is usually the commit just before the first commit you want to modify. For example, if you want to squash commits D, E, F on your feature X branch, and C is their parent. A B, C, D, E, F main, feature X. You would run git rebase icssha hash the sha one of commit C. Hash, or more commonly, go back a certain number of commits from head. Git rebase ihead ~3 hash to rebase the last 3 commits. An interactive editor opens. Git will open your default editor, e.g., Vim, VS Code, with a list of the commits you selected, in reverse chronological order like this. Pick D41B23, F add component sketch. Pick EC5D6F, 7A fix typo in component name. Pick FA8B9C0D, add basic styling to component. Hash rebase 2D18228. A8B9C0D onto C7B8D9, E3 commands. Hash commands. Hash P, pick commit equals use commit. Hash R, reword commit equals use commit, but edit the commit message. Hash E, edit commit equals use commit, but stop for amending. Hash S, squash commit equals use commit, but meld into previous commit. Hash F, fix up commit equals like squash, but discard this commit's log message. Hash X, exec command equals run command, the rest of the line, using shell. Hash D, drop commit equals remove commit. Hash L, label equals label current head with a name. Hash T, reset label reset head to a label. Hash M, merge C commit label hash 1 line. Create a merge commit and reset the original head. Hash these lines can be reordered. They are executed from top to bottom. Hash if you remove a line here, that commit will be dropped from the series. Hash, rest of Git's help message. Edit the commands. To squash E and F into D. Change pick to squash or S. For E and F pick D41B23 F add component sketch. SEC5D6F, 7A fix typo in component name. SFA8B9C0D, add basic styling to component. To reword D's message. change pick to reword or R, to edit amend D, change pick to edit or E. Git will pause and let you make changes before continuing the rebase. To drop F, delete the line for F save and close the editor. Git will then execute the commands. If you squashed commits, it will open another editor for you to write the new, combined commit message. Interactive rebase gives you fine-grained control over your branch's history, allowing you to present a clean, concise, and logical set of commits when you finally merge into main. Git cherry-pick, applying individual commits. Sometimes, you only need one or two specific commits from another branch, not the entire branch. Git cherry-pick allows you to apply, copy, specific commits from any branch onto your current head. Scenario: a critical bug fix, commit X, was made on feature X, but feature X is not ready to be merged into main. Main needs that fix immediately. A BCF main \dexy feature X. To apply commit X onto main, git switch main, git cherrypick XSHA. This will create a new commit X on main that is identical to X, but with a new SHA1 hash, without bringing in D, E, or Y. A BCFX main \dexy feature X. Cherrypick is useful for hotfixes, or for moving changes between branches when a full merge isn't appropriate. Conflicts can occur and are resolved similarly to rebase conflicts. Strong warning: never rebase shared history. We can't stress this enough. If a commit has been pushed to a remote repository and someone else has pulled that commit, do not rebase the branch containing that commit. Rewriting history that others rely on will cause chaos and frustration. If you need to undo changes on a shared branch, use git revert. If you need to clean up commits on a branch before pushing it, then git rebase I is perfect. If you need to update a feature branch with main's latest changes, and you haven't pushed your feature branch yet, then git rebase main is a good choice. If you have pushed your feature branch, git pull rebase, which is a fetch followed by a rebase, is generally safer for personal feature branches, but only if you are extremely sure no one else has pulled your feature branch yet. Consider git merge instead if there's any doubt. Summary and looking ahead. Git rebase is a powerful tool for maintaining a clean, linear project history. You've learned how rebase differs from merge by rewriting history, when to use rebase, tidying local history, keeping feature branches updated. The critical rule: never rebase shared history. How to perform a simple rebase and resolve conflicts during the process. The versatility of git rebase, I for squashing, editing, and reordering commits. The targeted application of git cherrypick. While rebase requires a solid understanding and careful usage, its benefits in maintaining clean, readable history, especially in complex projects, are significant. In the next chapter, we'll dive into advanced topics and best practices, covering useful Git features like tagging, stashing, aliases, and hooks, and reinforcing good habits for efficient version control. Chapter 10. Advanced Topics and Best Practices. Introduction: polishing your Git skills. You've now mastered the core commands of Git, from initializing repositories and making commits to managing branches, merging, rebasing, and interacting with remotes. You also have a good grasp of how to recover from common mistakes. This chapter builds on that foundation, introducing several advanced Git features that can significantly enhance your workflow, along with crucial best practices that foster better collaboration and maintain cleaner project histories. These tools and habits will help you to be more efficient, organized, and a more effective Git user. Tagging releases. Git tag. Tags in Git are like permanent, unmoving pointers to specific commits. Unlike branches, which move forward with new commits, a tag always points to the exact same commit it was created on. This makes them ideal for marking important points in your history, such as release versions, e.g. v1.0.0, v2.1 beta. There are two main types of tags: lightweight tags, essentially a pointer to a commit. Just a file containing a commit's SHA1 checksum. Doesn't store any extra information, like author, date, message. Often used for temporary or private tags. Creation: git tag tagname, e.g. git tag v1.0 alpha. Annotated tags, full Git objects stored in the Git database, contain a checksum, who created the tag, when it was created, and a tagging message. can be GPG signed and verified, highly recommended for production releases. Creation. Git tag a tag name m tag message, e.g. git tag av 1.0.0 m release version 1.0.0 stable production. Git will open your default editor if m is omitted. Common tagging commands list all tags. Git tag #v 1.0 alpha #v 1.0.0 list tags matching a pattern. Git tag lv1 create a tag on a specific past commit. Append the commit's SHA1 or a reference, e.g. branch name, to the tag command. Git tag AV 0.9.0 m initial public release fa0b5c1 show information about a tag. Git show tag name. Git show v 1.0.0. This will show the tagger information, the tag message, and the commit information that the tag points to. Push tags to a remote. By default, git push does not push tags. You must push them explicitly. Git push origin tag name #push a single tag. Git push origin tags #push all your local tags. Delete a local tag. Git tag d-tag name. Delete a remote tag. Git push origin ref/tag/tag name or git push origin delete tag name. Stashing temporary changes. Git stash. Imagine you're working on a feature branch. You have some changes that are not ready to be committed, but you urgently need to switch to main to fix a bug or pull in an update. You don't want to commit incomplete work, a work-in-progress commit, and you don't want to lose your modifications. Git stash is your answer. Git stash takes your modified tracked files and staged changes, saves them on a stack of unfinished changes, and then cleans your working directory back to the state of your last commit. Common stashing commands. Save your changes. Git stash save work in progress on new feature, #add a message for clarity. Or simply, git stash. After running git stash, your working directory should be clean like git status shows. Nothing to commit, working tree clean. List your stashes, git stash list. #stash at 0, on feature new design, work in progress on new feature. #stash at 1, on main, minor bug fix attempt. Apply a stash, and keep it in the stash list. Git stash apply # applies the most recent stash at 0. Git stash apply stash at 1, # apply a specific stash. Apply leaves the stash in your stash list, so you can apply it multiple times or to different branches. Conflicts can occur when applying a stash, just like with merges. Apply a stash and remove it from the stash list. Git stash pop # applies the most recent stash at 0, and drops it. This is generally the preferred method when you intend to apply a stash only once. Show differences of the latest stash. Git stash show. Git stash show, p # show full diff. Delete a stash. Git stash drop # deletes the most recent stash. Git stash drop stash at 1, # delete a specific stash. Delete all stashes. Git stash clear. Create a branch from a stash. This is useful if you stash changes and then realized they should have been on a new branch. Git stash branch new feature branch stash at 0. This command creates a new branch named new feature branch, switches to it, pops the specified stash, and then removes the stash from your stash list. Git aliases, customizing your command line. Git can be quite verbose, and some commands or combinations of flags are used frequently. Git aliases allow you to create shortcuts for common commands, saving keystrokes and making your workflow more efficient. You can add aliases directly to your Git configuration. Configure an alias. Git config global alias.co checkout. Git config global alias.br branch. Git config global alias CI commit. Git config global alias sent status. Git config global alias LG log color graph pretty equals format. %cred %h %cresset. C yellow D cresset %s %c green %cr. %c bold blue and %cresset, a brief commit. Git config global alias unstay, restore staged. Git config global alias visual, git hash for git. Now, instead of git checkout, you can type git co, and git lg will give you a beautifully formatted log. An alias starting with executes the command as a shell command. You can modify these or remove them using git config global unset alias lg as you find your own preferred shortcuts. Git hooks automating tasks. Git hooks are scripts that Git automatically executes before or after certain events, such as committing, pushing, or receiving pushed commits. They are powerful tools for automating quality checks, enforcing policies, or integrating with other systems. Hooks are stored in the Git hooks directory of your repository. Git provides template scripts, ending in sample, that you can rename and modify. Common hooks, pre-commit, runs before a commit message is even generated. If this script exits with a non-zero status, the commit is aborted. Use cases: linting code, running unit tests, checking for large files, verifying commit message format. Prepare commit MSG runs after the default commit message is created but before the editor is launched. Use cases: automatically populating commit messages based on branch names or issue trackers. Post-commit runs after a commit is successfully created. Use cases: notifying integrated systems, updating a project management tool. Pre-push runs before Git push transfers commits to the remote. If it exits with a non-zero status, the push is aborted. Use cases: ensuring all tests pass, preventing pushes to main directly. Post-receive on remote server runs on the remote server after a successful push. Use cases: deploying code, triggering CI/CD pipelines, updating a dev environment. Example: pre-commit hook in Git hooks pre-commit /bin/sh, a simple pre-commit hook that checks for a specific TODO pattern and prevents commit if found. If grep q TODO, git diff cached name only, then echo error, remove TODO. Comments before committing: exit 1, phi, make the script executable. chmod + x git hooks pre-commit. Now, if you try to commit a file with TODO in it, the commit will be rejected. Important considerations for hooks. Hooks are local to each repository. They are not version controlled or pushed with your code by default. If you want to share hooks with a team, you typically need a system to manage them, perhaps by creating a hooks directory in your main repository and a script that users can run to link them to Git hooks. Hooks can be bypassed by git commit no verify or git push no verify. Choosing and using Git GUI tools. Brief overview. While the command line provides the most control and understanding, graphical Git clients offer visual aids that can simplify complex operations, especially for beginners or for quick reviews. Popular Git GUI tools include Git Kraken, a popular, modern, cross-platform GUI with a beautiful interface and robust features. SourceTree, a free Git client for Windows and Mac, visually rich and popular in enterprise settings. GitHub Desktop, simple, clean, and tightly integrated with GitHub, great for basic Git operations. SmartGit, a powerful, cross-platform client with a comprehensive feature set. Integrated IDE clients. Many modern integrated development environments, IDEs like VS Code, IntelliJ IDEA, WebStorm, and Visual Studio have excellent built-in Git integration, often with visual diff merge tools and interactive commit staging. These are often the most convenient for daily use. Experiment with different GUIs to find one that suits your workflow. However, always strive to understand the underlying Git commands first, as this knowledge will empower you regardless of the tool you use. Best practices: elevating your Git game. Adopting good practices will make your work more efficient, your history more understandable, and collaboration smoother. Atomic commits. Each commit should represent a single, logical change. Don't lump unrelated changes into one commit. Good: fix styling on product page, add unit tests for user authentication. Bad: fix A, add B, improve C. Why? Makes history easier to read, revert, and understand. Aids in debugging, e.g. with git bisect. Meaningful commit messages. Summary line, concise, imperative, 50 to 72 characters, e.g. fix. Prevent null pointer exception. Body, explain why the change was made, what problem it solves, and how asterisk gets implemented if necessary. Wrap lines at 72 chars. Why? Improves readability, allows colleagues and future you to understand quickly, aids in searching history. Frequent commits. Commit often, even small, incomplete changes. It's easy to squash or amend commits later. Fewer commits means more information lumped together, making it harder to revert specific items. Why? Provides more granular control, easier to recover from mistakes, acts as frequent save points. Keep branches short-lived, especially feature branches. Merge them back into main or develop as soon as the feature is complete and reviewed. Why? Minimizes merge conflicts, keeps feature branches from diverging too much, promotes continuous integration. Pull frequently. When collaborating, Git pull or Git fetch and Git merge regularly to get the latest changes from your teammates. This reduces the chances of large, complex merge conflicts. Why? Early detection of potential conflicts, smoother integration. Use Git ignore effectively. Keep your repository clean by ignoring generated files, dependencies, and editor configs. Why? Prevents accidental committing of irrelevant files, keeps repo size down, cleans Git status output. Review Git status and Git diff before committing. Always know exactly what you're about to commit. Why? Catches mistakes before they are etched into history. Understand rebase versus merge. Choose the right tool for the right job, and strictly adhere to the never rebase shared history rule. Why? Prevents catastrophic history divergence and team frustration. Summary and looking further. This chapter has provided you with a powerful set of tools and a mindset for using Git effectively. You've learned about using Git tag to mark significant points like releases, leveraging Git stash to manage temporary work in progress, customizing Git commands with Git alias, automating workflows and quality checks with Git hooks. The options available in Git GUI tools. Crucial best practices for a clean, efficient, and collaborative Git workflow. You now have a comprehensive understanding of Git's capabilities. In the next chapter, we'll explore different Git workflows that teams adopt, from simple feature branching to more structured approaches like Git flow, and discuss how to choose the right one for your project. Chapter 11. Popular Workflows and Strategies. Introduction. Orchestrating collaboration with Git. You've mastered Git's core commands and even some advanced techniques. You understand how individual commands like branch, merge, and rebase work. But how do teams of developers, each making their own changes and working on different features, coordinate their efforts to maintain a coherent and stable codebase? This is where Git workflows come in. A Git workflow is a guide or a set of rules on how to use Git to achieve a consistent and productive development environment. There's no single best Git workflow. The ideal choice depends on your team size, your project's nature, release frequency, and desired level of rigidity. This chapter will explore some of the most popular Git workflows, outlining their structure, advantages, and ideal use cases. We'll examine the feature branch workflow, Git flow, and GitHub flow GitLab flow, and discuss how to choose the right strategy for your team. Feature branch workflow. Simple and widely used. The feature branch workflow is arguably the most common and simplest Git workflow, and it's the one we've implicitly used in previous chapters. It centers around the idea that all feature development should happen on dedicated branches rather than directly on the main or master branch. How it works. Main branch is stable. The main branch is always kept stable and potentially deployable. All development work occurs in parallel feature branches. Create feature branch. For each new feature or bug fix, a new branch is created from the main branch. Git switch main. Git pull hash ensure main is up to date. Git switch C feature new shopping cart. Develop in isolation. Developers work on their feature branch, making commits and pushing them to the remote feature branch. Hash work add commit frequently. Git push origin feature new shopping cart. Pro tip: occasionally rebase your feature branch onto the latest main or develop to pull in new changes and resolve conflicts early. Git switch feature new shopping cart. Git rebase main hash or Git merge main if rebase isn't preferred. Integration pull merge request. Once the feature is complete and reviewed, it's merged back into main. This is typically done via a pull request on GitHub/Bitbucket or merge request on GitLab. These platforms provide a web-based interface to review code, run automated tests, and discuss changes before integrating. The merge into main can be a fast-forward merge, if main was always ahead of the feature branch, or if the feature branch was rebased onto main just before the merge, or a standard three-way merge. Cleanup. After the merge and deployment, if applicable, the feature branch can be deleted locally and remotely. Advantages: simplicity, easy to understand and implement, making it suitable for teams new to Git. Isolation. Development on features remains separate from the main codebase, reducing risks. Encourages pull requests, naturally integrates with code review processes via platforms. Flexible history can result in either a clean, linear history with rebase and fast-forward merges, or a merge-inclusive history with Git merge. Disadvantages: lack of structure. Can become less clear for larger projects or teams without clear guidelines, as there's no defined branch lifecycle. Merge overhead. If feature branches are long-lived and main changes frequently, merging can become complex. Best for small to medium-sized teams, projects with continuous delivery, open-source projects, where contributors create feature branches forks. Git Flow, a prescriptive branch management model. Git Flow, introduced by Vincent Dreesen in 2010, is a more robust and opinionated branching model suitable for larger teams and projects that require strict release management and support for multiple versions. It defines a rigid set of branches with specific purposes. Git Flow branches, main or master, the only branch with production-ready code. New commits are only added via merges from release or hotfix branches. Tags indicate official releases. Develop, the main development branch. All feature branches eventually merge here, represents the current state of the next release. Feature name branches, created from develop. Used for developing new features. Merge back into develop when complete. Release version branches, created from develop when develop has enough features for an upcoming release. Used for bug fixes specific to the release, final testing, and metadata adjustments, e.g. version numbers. Once stable, merged into both main and tagged and develop to ensure develop has the latest fixes. Hotfix name branches, created directly from main to address critical bugs in production, merged back into both main and tagged and develop to carry the fix forward. Git Flow workflow steps simplified. Initialize. Git Flow init command available via Git Flow extensions. Start feature. Git Flow feature start new login creates feature new login from develop. Develop feature, work on feature new login. Finish feature. Git Flow feature finish new login, merges feature new login into develop and deletes the feature branch. Start release. Git Flow release start 1.2 creates release 1.2 from develop. Prepare release. Perform bug fixes and final touches on release 1.2. Finish release. Git Flow release finish 1.2 merges release 1.2 into main and tags it and develop, then deletes release 1.2. Start hotfix. Git Flow hotfix start crucial bug creates hotfix crucial bug from main. Fix bug, work on hotfix crucial bug. 10. Finish hotfix. Git Flow hotfix finish crucial bug merges hotfix crucial bug into main and tags it and develop, then deletes hotfix crucial bug. Advantages: structured and predictable. Clear roles for each branch and well-defined processes. Supports parallel development. Multiple feature teams, releases, and hotfixes can be managed concurrently. Good for iterative releases. Excellent for projects with scheduled release cycles and hotfix requirements. Version support. Simple to maintain multiple versions of the code, e.g., for different customer deployments. Disadvantages: complexity. Can be overly complex for smaller teams or projects without strict release cycles. Less agile. The rigidity might feel restrictive for teams focused on continuous delivery. Dual main develop branches. Can sometimes lead to confusion or extra merging. Best for larger teams, enterprise projects, projects with strict release management, legacy systems, multi-version support. GitHub Flow/GitLab Flow. Simpler, continuous delivery-focused models. These flows are variations of the feature branch workflow, specifically tailored for continuous delivery or simpler, more agile development, often leveraging the capabilities of their respective platforms, GitHub GitLab. They prioritize simplicity over the strictness of GitFlow. GitHub Flow. GitHub Flow is exceptionally simple, with only one main long-running branch, main or master. How it works: main is deployable. The main branch is always in a deployable state. Create branches. For anything new features, bug fixes, experiments, create a new branch from main with a descriptive name. Git switch main. Git pull. Git switch, see add login form. Commit and push. Make commits and push regularly to your branch. Open a pull request. When work is ready or you need feedback, open a pull request, PR to main. This triggers code reviews, CI/CD, and discussions. Review and merge. Once the PR is approved and passes all checks, it's merged into main. The feature branch is then deleted. Deploy. After the merge to main, deploy to production immediately. Advantages: simplicity, very easy to learn and follow. Continuous delivery, naturally supports frequent deployments to production. Platform native. Works seamlessly with GitHub's pull request model. Reduces merge conflicts. With frequent small PRs and immediate deployment, large conflicts are rare. Disadvantages: no release branches. Not ideal for projects that need to support multiple versions or structured release cycles. Hotfixes. Hotfixes are just another branch from main, merged quickly, which isn't a problem, but it lacks specific labeling as Git flow. Best for web applications, SaaS products, teams focused on rapid iteration and continuous delivery, where the main branch is always ready for deployment. GitLab Flow. GitLab Flow extends GitHub Flow by adding environment-specific branches, like pre-production, production, and optionally release branches for larger projects, while still maintaining high integration with GitLab's platform features. How it works with environment branches. Main is stable. Similar to GitHub Flow, main is generally considered stable. Feature branches. All feature development happens on branches created from main. Merge into main. Features are merged into main via merge requests, GitLab's equivalent of PRs. Deployment into environment branches. Rather than deploying directly from main, main is merged into environment branches, e.g., pre-production, production. Main pre-production, production. This provides environments for testing and staging before going live. Hotfixes can merge directly into production and then into main. Advantages: balancing simplicity and control. Offers more structure than GitHub Flow, but less complexity than Git Flow. Staging environments. Excellent for projects with dedicated staging and production environments. Strong CI/CD integration. Designed to integrate with automated pipelines for deployments. Disadvantages: can still be tricky for maintaining multiple long-term release versions. Best for teams that want a streamlined workflow but need distinct staging environments before production. Large-scale web applications. Choosing the right workflow for your team. Selecting a Git workflow is a key decision that impacts team collaboration, release cycles, and overall project stability. Consider these factors: team size and experience. Smaller, more agile teams might thrive on simpler workflows like GitHub Flow, while larger distributed teams might benefit from the structure of Git Flow. Project type and release cadence. Continuous delivery, CD. If you're deploying multiple times a day, GitHub Flow or a simplified GitLab Flow is ideal. Scheduled releases. If you have strict release cycles, e.g., monthly, quarterly, and need to support multiple versions, Git Flow might be a better fit. Hotfix frequency. How often do you need to push emergency fixes to production? Workflows should accommodate this. Strictness versus flexibility. Do you need a rigid, defined process, Git Flow, or a more flexible, adaptive approach, feature branch GitHub Flow? Testing philosophy. How do changes get tested before production? Do you need dedicated staging environments, GitLab Flow? Familiarity with Git. Simpler workflows are easier for newcomers to grasp. Case study. A fictional team adopts a Git workflow. Imagine the Innovate Now dev team, a small, agile startup building a SaaS web application. They initially started with no formal Git workflow, just everyone committing to main. This quickly led to broken builds and frantic hotfixes. Initial chaos. Main was often unstable. Many conflicts, no code review. Adoption of feature branch workflow, phase 1. The team implemented a basic feature branch workflow. Everyone created branches for new features bug fixes. They used pull requests on their GitHub repository for code review, with main being deployable. This cleaned up main significantly. Scaling and CI/CD needs. Phase 2 transition to GitHub Flow. As the team grew and started aiming for daily deployments, they noticed that merging into main and then manually deploying caused delays. They transitioned to a stricter GitHub Flow, where every merge into main automatically triggered a CI/CD pipeline and an immediate deployment to the staging environment. Once confirmed, a manual trigger deployed to production. This enabled rapid iteration. Consideration of GitLab flow future. If Innovate now grows to have multiple distinct production environments or needed release candidates, they might consider adopting a GitLab flow to manage separate environment branches more formally. This case study demonstrates that workflows can evolve. What works for a small, greenfield project might not scale to a large, mature product with complex release requirements. The key is to understand the trade-offs and evolve your workflow as your needs change. Summary and going further. Choosing and implementing the right Git workflow is crucial for the success of any collaborative software project. You've now gained insight into feature branch workflow, simple, flexible, common for teams using pull requests. Git flow, a structured, prescriptive model ideal for projects with distinct release cycles and multi-version support. GitHub Flow/GitLab Flow, simpler models focused on continuous delivery and leveraging platform features for rapid iteration. Key factors to consider when choosing a workflow for your team. You now possess a comprehensive understanding of Git and its application in real-world scenarios. In our final chapter, we'll cover common troubleshooting scenarios, explore some niche features, and guide you on resources for continuous learning, ensuring you can navigate any Git challenge and continue to deepen your expertise. Chapter 12, Troubleshooting and Going Further. Introduction, Mastering the Unpredictable. Congratulations! You've navigated through the core concepts, daily commands, and advanced techniques of Git. You've learned how to harness its power for individual work and collaborative projects, and you even know how to pull your repository back from the brink of disaster. But like any powerful tool, Git can sometimes present unforeseen challenges. Even with a solid understanding, you'll inevitably encounter situations that leave you scratching your head. This final chapter aims to equip you for those moments. We'll cover common problems and their solutions, introduce a powerful debugging tool, Git Bisect, briefly touch upon Git submodules, and most importantly, guide you on how to continue your journey of learning and mastery with Git. Common problems and their solutions. Before diving into complex scenarios, let's address some of the recurring issues beginners and even experienced users face. Nothing to commit, working tree clean after making changes. Problem. You've made edits, but Git status says there's nothing to commit. Reason, you forgot to add your changes to the staging area, or Git might be ignoring the files see git ignore below. Solution. Check Git status for changes not staged for commit or untracked files. Use git add file or git add to stage them. Failed to push some refs to. Updates were rejected because the remote contains work that you do not have locally. Problem. Git won't let you git push your changes. Reason, someone else has pushed new commits to the remote branch since you last pulled. Your local history has diverged from the remote. Solution. First, git pull to fetch the remote changes and merge them with your local branch. Resolve any merge conflicts that arise, Chapter 6. Then, try git push again. Detached head state. Problem. You've checked out a specific commit, e.g. git checkout commit hash or a tag, and git status says head detached at commit hash. Reason, your head pointer is directly on a commit, not a branch. Any new commits you make in this state will not belong to a branch, potentially becoming lost. Solution, if you just wanted to view history, git switch branch name, e.g. git switch main to return to a branch. If you made commits in this state and want to keep them. Git switch c new branch name creates a new branch from your detached head's current commit, and subsequent commits will extend this new branch. You can then merge this new branch into your main development line. If you don't care about the changes, git restore. Before switching back to main could also work, just git switch main to abandon new edits made on a detached head. Large files in Git. Problem. Your repository size is huge, or git push is slow because of large files, e.g. binaries, videos, large datasets. Reason, Git is designed for text-based code. It doesn't handle very large binary files efficiently. Committing large files directly into history, even if they are later deleted, bloats the repository permanently. Solution, prevention. Use git ignore to prevent large binary files from ever being committed. Git LFS, large file storage. For tracking large files within Git, use Git LFS. It replaces large files with small pointer files in your repository, while the actual file contents are stored on a remote LFS server. Cleaning history. If large files are already committed, you'll need advanced techniques, like Git filter repo or BFG repo cleaner, to rewrite history and remove them. This is a complex operation and permanently changes your repo's history, so it should only be done on private repos or with careful coordination with all collaborators. Accidentally committed sensitive information, API keys, passwords. Problem: you pushed a commit containing a password or API key to a public repository. Reason: oversight. Solution: first, invalidate the credential immediately. Change the password, revoke the API key. Assume it's compromised. Second, rewrite history to remove it. This is a critical step, but it's complex and, like large file removal, will change commit SHAs. Use Git filter repo or BFG repo cleaner. This is history rewriting. You must coordinate with all collaborators who have pulled that branch to force update their local repositories. Prevention. Use environment variables, secure configuration management systems, and pre-commit hooks to check for secrets. Debugging with Git bisect. Git bisect is an incredibly powerful Git command for finding the specific commit that introduced a bug or a regression. It uses a binary search algorithm to quickly narrow down the range of commits. You tell Git which commit is good, where the bug didn't exist, and which is bad, where the bug does exist, and Git automates the process of checking out commits in between. How it works: start bisecting, Git bisect start. Mark a bad commit, this is where the bug is present. Usually this is your current head. Git bisect bad. Mark a good commit, this is a known commit where the bug did not exist. Git bisect good commit hash. Git will then automatically check out a commit roughly halfway between the good and bad commits. Test the code. Run your tests, manual or automated, on the currently checked out commit. Tell Git the result. If the bug is present, Git bisect bad. If the bug is not present, Git bisect good. Git will continue to check out intermediate commits, narrowing the search range. Git finds the culprit. Eventually, Git will tell you the exact commit that introduced the bug. Commit hash is the first bad commit. Author, date, commit message. Reset. After finding the bug, always reset Git's state. Git bisect reset. This returns you to your original branch. Git bisect can save hours of manual debugging, especially in projects with long and complex histories. Working with submodules. Brief overview. Sometimes, a project needs to embed another project within it, but you want to keep the two projects as separate entities. For example, your main application might depend on a specific library or a third-party plugin that is also a Git repository. Git submodule allows you to achieve this. A submodule essentially records a specific commit from an external repository within your main repository. Adding a submodule. Git submodule add https github.com/example/my-library vendors my-library. This clones the my-library repository into the vendors my-library directory within your project and adds a Git modules file to track it. Cloning a project with submodules. After cloning the main repository, you need to initialize and update the submodules. Git submodule update init recursive. Updating submodules. To pull in the latest changes from the submodules remote. Git submodule update remote vendors my-library. Caution: submodules can be complex to manage, especially when updates are frequent or multiple team members are involved. They can lead to detached head states within the submodule, and care is needed to ensure the parent module always points to the correct submodule commit. Alternatives like package managers, NPM, Composer, Maven, etc., or monorepos are often preferred if the relationship is just a dependency. Resources for continuous learning. The journey to Git mastery is ongoing. Here are some excellent resources to continue your learning. Official Git documentation, Pro Git book. The Pro Git book, available online for free at https://git-scm.com/book/, is the definitive guide. It covers everything from basics to advanced topics in immense detail. Git official website, https://git-scm.com, provides downloads, documentation, and a command reference. Atlassian Git tutorial. Atlassian, creators of Bitbucket and Jira, offers excellent, visually rich tutorials on virtually every Git concept and workflow. https://www.atlassian.com/git/tutorials. GitHub Docs and GitLab Docs. The documentation for these platforms often contains practical guides and best practices for common workflows on their systems. Online courses and platforms. Websites like Udemy, Coursera, Pluralsight, and many others offer in-depth video courses on Git, ranging from beginner to expert level. Git communities. Stack Overflow is an invaluable resource for specific Git error messages or challenging scenarios. Online forums and developer communities are also great for asking questions and sharing knowledge. The future of Git and version control. Git's fundamental design principles, distributed nature, cryptographic integrity, snapshot model, and powerful branching ensure its continued relevance. While new features and commands are regularly added and tools evolve, the core concepts remain stable. The trend for version control is towards tighter integration with development tools, continuous integration delivery pipelines, and more intuitive graphical interfaces that abstract away some complexity. However, the command line will always remain the most powerful and versatile way to interact with Git. Git has become, for many, an indispensable tool. It shapes how teams collaborate, how software is built, and how work is managed across countless industries. Its impact extends far beyond just code, influencing practices in documentation, design, and even scientific research. By understanding Git's mechanics, mastering its commands, and applying best practices, you're not just learning a tool. You're gaining a fundamental skill for navigating the complex, collaborative, and ever-changing landscape of modern digital projects. Conclusion: you now possess the knowledge to confidently use Git in your personal projects and actively participate in team environments. You're equipped not just with commands, but with the understanding of why Git works the way it does, empowering you to troubleshoot and adapt. The journey ahead will involve more practice, continuous learning, and sharing your knowledge. Embrace the power of Git. It will serve you well in your endeavors.